Well, hi, I'm Dan Holohan, and I'm here to talk with you about Classic Hydronics, one of my favorite topics in all the world. And I'm going to teach you some old stuff, some new stuff, and it's kind of a liberal arts approach to hydronics. And mostly I want you to see these principles in your mind's eye, because if you can do that, you can solve any problem. So walk with me, because I'm not an engineer, and I don't talk like an engineer, but I think in pictures. So let's do that together. Here's a couple of pictures for you. Stop and go. When I was learning about hydronics, an old timer said to me, there's only one arrow in the system that you could trust, and that's the arrow on the circulator. So go find that, because everything else might be put on backwards. And I got a kick out of that. But then as the years went by and I visited jobs, I realized how true that was, because you go out there and you'll see these stickers that go onto pipes put on by human beings. They'll say heating return, and in hot water return, one goes left, one goes right. So I started to wonder about that, and one time I was troubleshooting a job with a guy, and the arrows had been put on backwards, and he makes me a sketch, and he's showing me where the water's going, and I'm looking at the job, and it's just not what I'm seeing. So I said to him, did you read the instructions that came with those markers? And he says, what are you talking about? I said, well, they're made by a company mostly called Setmark, and they publish the instructions, and it's important always to read the instructions, because if you look right here at the bottom, you can see that it says, caution, to ensure proper operation, always install arrows on the insides of the pipes, so you'll know that the water will know the direction you've chosen for it to move. Otherwise, it's not going to know. So we had a good laugh over that, and I hope you did too. But when I was learning this stuff, I had many old-timers talking to me, and one of them said to me, Dan, if you really want to understand this, you got to kind of think like water and imagine that you're inside the pipe. And one good way to imagine you're moving through the pipe is to think of yourself as a marble. And when you're inside the pipe, just think about what you would do if you were the marble. So I kind of liked that because it was real visual. And then he said to me, okay, you're going down the pipe, and you could feel what it's like where the outer edge of the water is rubbing against the inside of the pipe, but the inside of the water flow is kind of getting a free ride because it's not touching any of the pipe. But then you get to an elbow, and what happens? And I thought about this for a second, and I'm thinking bumper cars, and imagine the water comes zooming in here, and it smashes into this wall to make this turn, and suddenly you've got all this turbulence going on inside here, and more of the water touches more of the pipe, so there's more friction. And I saw that so clearly in my mind, and then he said to me, okay, this is a friction flow chart, and let me show you how far water can go in a straight pipe compared to how far it can go through just one elbow. So he was showing me the difference between the friction loss of an elbow and the friction loss of a pipe, but thinking of myself as a marble made it so much clearer. So he took it a step further with me, and he said, okay, that's one fitting. Now here's another fitting for you. It's a T. You're going to go into a T, and what's going to happen then? And I said, well, I guess I'm going to come out. He says, yeah, but which way? And as time went by, again, I had a teacher I'll tell you about later on, more about him, because he was a great guy in hydronics. His name was Gil Carlson, and much of what we take for granted these days is attributed to him and his brilliance. But Gil used to talk about the law of the T, and he'd sit in rooms with engineers, and he'd be lecturing, and he'd say, the law of the T, and everybody would grab for a pencil to write down. He says, it works like this. Whatever goes into a T must come out. And people would stop and look at him, and he'd just smile at them. But it was so true. Whatever goes in must come out. But how will it come out? That's really what's going to make the difference on the job. Does it go straight or does it turn? So from there we expanded to this thing that the engineers talk about, and it's a Greek letter delta, which means change in engineering, and P stands for pressure. So when we talk about delta P, we're talking about a change in pressure, and this is really what drives all of hydronics and so much of life. I mean, it's what makes the weather work. When you're watching a weather report and you hear the weatherman talking about there's a high pressure area coming in, the weather's going to be good. Or if he says there's a low pressure area coming in, it's going to be stormy. And that's because if we're sitting in a low pressure, we're going to have wind because there's a high pressure somewhere else in the country that's going to rush in to fill the low pressure. So that's, in my mind's eye, it's easy to understand. But what's even easier to understand when you're thinking about delta P is a trip to the gas station. Because you go to the gas station, you want to not just get gas, but you want to check the air in your tires. And you know, in Long Island where I live, the air used to be free. You go up there and you pump it, but then they decided they could charge for this. So first they started to charge a quarter, and then they charge 50 cents. Next thing you know, they're charging $1. And I think they've got the machine set so that it'll do 3 tires, you know, on $1, and you got to put in another 4 quarters to get the 4th tire. But I often wonder when I'm putting the air in the tires, like how does that compressor know that that tire is full? Because there's no electrical wiring between the tire and the compressor. You just stick the hose onto the Schrader fitting in the tire, and it goes ka chunk, ka chunk, ka chunk, ka chunk, ka, and now you know you're done. So you pull the hose off and it goes chunk. You never get the last chunk in there, even though you paid for it. But I wondered, like, how does that compressor know that the tire is full? And the more I stood there thinking about it, the more I realized that it knows because the pressures are equal. Whatever's in the compressor is now in the tire, and when pressures are equal, there's no movement. So this applies to hydronics too, because if there's no difference in pressure between 2 points, there's not going to be any flow of water. So we see it at the gas station, we see it in the weather, and you know, it's just about everywhere. So you think about these basic principles. High pressure goes to low pressure always. If you get the basic principles in your head, you could troubleshoot and solve any kind of hydronic problem. For instance, think about this helium balloon. You let it go, it's going to go up higher and higher and higher, and it's going to get to a point where it won't go any higher. And think about what's making that balloon go up. And you know, when I ask guys that, they'll say, oh, because it's lighter than air. Yeah, and that's true if you're thinking in terms of the balloon itself, but think about what's on the outside of the balloon, which is the atmosphere. It's the air itself. And what's really at work here is not so much the balloon going up, it's the air falling down. What's making that balloon go up is a very simple principle that we call gravity. So gravity plays a huge part in hydronics as well, and always has, and right back to the very beginning. For instance, let me show you a picture of the very first hydronic job ever done. And it was done not in America, but in Paris. It was done when America was not even yet quite America. We were fighting a revolution. It's in Paris in 1777, and it goes into an incubator. It goes into a hen house. We're trying to make chicken wings or hot wings for the Parisians. And this is the first time this is ever done. So this drawing alone should be worth the price of admission to you. But in this drawing, we see some of the basic principles that still apply to hydronics today. For instance, over here we've got, you know, what we would today call a boiler, but then was just a vessel that had a fire under it. Here are all the chickens sitting on their roosts. They got pipes going under them. And we're going to fill this system up by carrying water in buckets up to this funnel. So what we would today call a fill valve, in those days was a funnel. And these were real big pipes because we don't see circulators until 1923. So in 1777, they were depending purely on the laws of physics, primarily on gravity, that hot water is lighter than cold water. And when you heat water, the cold water is going to fall and the hot water is going to rise. So this is your first gravity system. But gosh, imagine those people that had to go to the well. There's no city water in 1777. Fill up buckets and carry it up to the top of this building and fill this whole thing up. So there's the fill valve, and look over here. We've got this pipe that comes over the top, and it goes into a tank to catch any excess water, because when we heat water, it expands, and suddenly you've got more water than you started out with when it's cold. So we have to have a place for that excess water to go. And up here at the top, you see the very first, what comes to be called the expansion tank. Now, an expansion tank is a tank that's open to the atmosphere. Nowadays, most of us use compression tanks. Those are the tanks that have diaphragms in them, or some of the older tanks didn't have diaphragms, but they had an air cushion. So if it's a compression tank, it's closed to the atmosphere and it's compressing air. And if it's an expansion tank, it's open to the atmosphere, as you see here, and it's just a place for the expanding water to go. So we go up out of the boiler with this pipe because hot water rises. And watch the way we come through here. It's like lacing a shoe. Just goes down under the hens over here. The hens are nice and warm now. They're going to lay us better eggs. Come back here all the way down to the end. These hens are happy here. And then watch the way the pipe goes down into the boiler through a dip tube. And that's very, very reminiscent of what we have in today's modern water heaters. Hot water comes out the top, cold water enters through the bottom because hot water rises. So within this 1777 drawing of the very first hot water heating system, you see all the principles that still apply today. So wrap your mind around the basics and you'll be able to troubleshoot just about anything. Oh, and think about this piping arrangement too. It doesn't really lend itself to zoning, does it? I mean, if you put a valve in anywhere, the heat stops everywhere, and you look at that and you say, who in their right mind would do that when they could do bypasses and zoning and all that? Who in their right mind? Well, you know who in their right mind, or maybe not in their right mind, but the Soviets did this in their huge housing projects that they allowed party members to live in. This is Moscow, and this is one of those Soviet apartment buildings. And because the heating was free for everybody, it was communism, they would come into a building like this and they would run the pipe. They go up to the top and they'd run the pipe all the way across this block of apartments and then come down to the next. No valves anywhere, no thermostats anywhere. The heat is on in the fall and goes off in the spring, and just heating all the way down like this, back and forth. People at the top get more heat than the people at the bottom, but that's the way it went. So go figure, right? And I was talking to some people who came from Russia, and I said to them, have you thought about zoning that, especially since the Iron Curtain fell? And they said, yeah, they talk about it, but it's too expensive to do, so they don't zone at all. And I said, well, how do they charge people now that they are charging people for the heat? And this one woman engineer said to me, well, the way it works is you pay for the amount of square meters that you have in your apartment space. And everybody pays based on how much space they take of the total fuel bill for the whole block. So I said, what does everybody pay? Are they good about that? She says, well, people are people, and sometimes they don't pay. And I said, well, what happens to that person? She says, well, what happens is the management will put a notice in the lobby. And first of all, they'll shut off all the heat for the whole building and the hot water. So nobody has heat, nobody has hot water. And then they put a notice in the lobby and in the stairways and the elevators, and they explain that you have no heat and no hot water because this person who lives in this apartment did not pay their bill. So I said, well, what happens then? She says, generally someone will kill that person. So that's great, right? That's a terrific way for accounts receivable. So welcome to Moscow. Gravity. Let me bring you back to the beginning. Because gravity hot water heat was very popular in America back at a time when the steam boilers were blowing up. Gravity hot water heat became very acceptable, particularly to the rich people. And in this system here that you see, the simplest gravity system, we have the basic laws of physics working. And within this, you'll see everything that is to follow. Everything is to come afterwards with hydronics. All the principles are here in this drawing. First of all, we've got 3 stories, and gravity wouldn't work any higher than that because when the hot water rises, it gives up its heat to the radiators, and after it goes up about 3 stories, it stops going up. So buildings that were taller than this were done with steam heat. But this is for rich people in houses, and they like the safety of it because it was vented to the atmosphere. Up here you see this tank. There's an expansion tank up in the attic. The pipe goes there, and the pipe also continues on outside the building. So it goes up to the expansion tank, which is then vented outside the building. So should the water get overheated, it's not going to explode, it's not going to cause pressure, it's just going to spill out onto the roof. They like that. The pipes had to be very large because we don't see circulators until 1923. So the larger pipes kept the friction down, because what we have here is in theory, a very simple system, but in practice and to install it, this is probably the most complicated hydronic system ever devised. Because since they didn't have circulators, they had to work with the pure laws of physics. And every pipe size, every angle mattered. Whether or not they reamed the pipe mattered. So they had to be very, very precise in the way they put this in. It was really a science. So big pipes, never higher than 3 stories. When they left the boiler, they would come out with multiple pipes. In this case, you see 2 rises coming up, 2 returns coming back. That's because the more exit space you gave for the hot water, the faster the building would heat. So they used multiple connections. And when they went out, they went first floor, second floor, third floor. And then you might ask, okay, which floor is going to get hot first? Is it going to be the first floor, the second floor, or the third floor? And most people I ask when they think about this, they say, well, the first floor, of course, because that's closest to the boiler. That should get hot first. But with gravity hot water heat, everything gets turned around and it's upside down because hot water rises. So here's the supply main. Look at this. You come through a T. The hot water is going to rise up, and then you come to another T over here, which turns to go into the radiator. Well, if you were hot water rising up this pipe, imagine yourself as a helium balloon being let go. You're not going to make that turn. You're going to go straight up to the top floor. So this was a challenge that they faced with these gravity systems because the path of least resistance was the top floor. So those were always the first floors to get hot. Second floor got hot next. First floor got hot last. It's exact opposite of what we would have with a pumped flow system. So this is a challenge. And if you're thinking about basic stuff like high pressure goes to low pressure, and you might go up to the top floor if you wanted to balance and throttle this valve up here. And if you throttle the valve, it makes it more difficult for the hot water to bust its way through that partially closed valve to get into the radiator. So some of that water is going to back up and go through the second floor and the first floor. But once again, we have to deal with people. So if you're up on the third floor with that tenant and you're closing down the valves and the tenant says, "What are you doing?" and you say, "I have to take away some of your heat to give it to the guy on the first floor," the tenant's going to say, "Oh, let me see how you do that." And he's going to watch what you're doing with the valve. And as soon as you leave the apartment, he's going to open that valve up wide again. You know that's going to happen because that's human nature. So the old timers had to find a way to get around that. And they did that by cracking this union connection here, right where the valve is connected to the radiator, and installing what's called an orifice. So an orifice is nothing more than a round plate with a small hole in it. And when they put the orifice in there, it built in a permanent resistance to flow through the radiator, which drove water down to the first floor and the second floor. And no matter what the tenant up here did with the valve, he doesn't know the orifice is in there because they kept that a secret. So that's how they balanced this system, by doing it just like that. And I found out about this the hard way because when I was younger and working for a manufacturer's rep, I would go out and help contractors and we'd look at jobs, and a lot of this old stuff that was on Long Island in New York would have these gravity systems. And a contractor I knew went out and changed the boiler, and he put in a modern boiler that had a circulator on it. And naturally, as soon as you add a circulator to the mix here, everything changes, because now with the circulator, the highest pressure is at the discharge of the circulator, and the lowest pressure is at the suction side of the circulator. So the water wants to find its easiest path, the path of least resistance, from its discharge side back to its suction side. So when the water leaves the boiler that now has a circulator on it, it's going to go right through the first floor and right back. And that's going to be helped by those orifices that are up here stopping the flow or slowing the flow to the top floor radiators. So my guy's on this job, and he says, I put the new boiler in, I can't get the top floors hot. So we do what most people do when they're young and they're just learning about this stuff. We went up to the top floor and we figured if there's no heat up there, it must be air. This has to be an air problem. So we go to the radiator and we start bleeding the radiators up here. And, we bleed. We get a little bit of air, but not much. And the radiator still won't get hot. So we do what most people do. We just keep bleeding the radiator because that's an instinct, right? We're compelled to bleed the radiator because we've got these keys and these cans and these rags, and we bleed and bleed and bleed. So finally we get frustrated because nothing's happening. So I went out and when I was younger, I knew that a good thing to do would be to collect old timers, because a lot of these guys were around when this stuff was put in when I was young. And they were dying off. So I would find people, and one of those guys was a man named Edwin Hicks, and he ran an oil company on the North Shore of Long Island where many of these Gold Coast mansions were. And I went in and I said to him, "Mr. Hicks, I'm working with somebody else, and this is what we did. We put in the boiler. It's got a circulator on it. It was a gravity hot water heating system. Can't get the top floor hot." And he says to me, well, Kitty, did you take the orifices out of the top floor supply valves and put them into the bottom floor supply valves? So I said, "Mr. Hicks, what's an orifice?" And he says, "Well, you're a stupid kid, I said, "Well, I never knew. I guess I am stupid." He says, "Well, take my advice." He says, "Take them out of the top floor radiators and put them into the bottom." And I never knew about these things because nobody told me. So we go there and pop the union, and sure enough, there's an orifice plate in there. So we take it out of there, we put it down on the first floor, and everything starts to work as it should. Who knew? The old timers never wrote it down. They kept it secret. So we learn a lesson as we go along, and it's a good one. Now notice here, too, that on these radiators, you see the way they're connected in the bottom and out the bottom? That's an old freestanding cast iron radiator. It's got a lot of water in it. It goes in the bottom and out the bottom. And I want you to stop for a minute and think like hot water. If you were hot water, what would you do? When you enter that radiator here, you're going to go in, and now you're hot. You're hotter than the stuff that's inside that radiator. So imagine yourself as the hot water. You come through that valve, and you're going to rise right to the top, displacing the colder water, which is going to fall by gravity down the pipe. This is why they went in the bottom and out the bottom on gravity hot water heating systems. It also made it a challenge when you're trying to vent these systems on startup, because if the system starts out empty and you're filling it, as you fill the system from the bottom, the water gets to this point, and you got to go up there on the first floor and open all these air vents to let the water fill the radiator. And then you got to do the same thing on the second floor and the same thing on the third floor. So you need more than one person to do this job to get it filled up just on startup. But now imagine, since we're going in the bottom and coming out the bottom, what's going to happen as soon as we add a circulator to this job. Because now when that comes on, again, think like water. You're under pressure, and you're trying to get back to the suction side of that circulator. So you come up this riser, and you go through the radiator, and right across the bottom, and down the other side, back down. So now, once again, it's a problem, because the bottom of the radiator is hot, and the top of the radiator is cold. So guess what you're going to do when you feel a hot bottom and a cold top? Right, you're going to bleed it. That's exactly what you're going to do. You're going to bleed it. And while you're bleeding, I want you to notice whether or not you get any air, because I guarantee you're not going to get any air once the system is full. You're just going to get cold water. But then you're going to continue to bleed. And you're going to bleed until you bleed all the water out of the radiator and make it hot. But then as soon as you leave, it's going to go cold again on the next cycle. So one of the things as we go through this course, I want you to remember is this. If you don't get any air when you're bleeding, it ain't an air problem. At this point, you must stop bleeding, because if you continue to bleed, you're going to be tricked into thinking that this is an air problem when it's not. It's actually a balancing problem. And balancing problem and air problems look like exactly the same from the outside. So I went back to Mr. Hicks and I said, how do I deal with this business where the water's going in the bottom and out the bottom when I've got a circulator? And he says, well, kid, here's another trick for you. If you want the radiator to get hot and you've added a circulator, you don't open the supply valve, you close the supply valve. Close it all the way down and just crack it a little bit. And that'll make the radiator hot. And I said, how is that possible? He says, well, again, think like water. You're trying to force your way into this radiator through the valve, but the valve's partly closed or almost fully closed. So you got to fight your way through there. And when you come out the other side, you got a lot less energy. So you're tired. When you're tired, what are you going to do? You're going to go take a rest. So you rise up to the top of the radiator, displacing the cold water, and it comes out the bottom. So we tried it, and you know what? Worked like a charm. So I learned a lesson there from that old man. May he rest in peace. Even in the basement on these gravity systems, look what they did. Knowing that hot water was going to stratify, since we didn't have a circulator moving it very quickly, the hot water would be at the top of the horizontal basement main. So they would connect the radiators for the upper floors to a 90-degree angle like this. And for the lower floors, the first floor, they would come off at a 45 because they wanted that to heat first. So you see the way the hot water has an easier time getting up through this connection than it does through this one. This is helpful if you're looking at an old job, because you could be in the basement and know where those pipes are going, to what floor, just by the angle that they take coming off. So if you see a 90-degree angle, that's going to an upper floor. 45-degree angle is always going to go to the first floor. Many manufacturers came out working with this principle, and they developed fittings like this. This was an odd one made by Phelps. It's empty on the inside, so the hot water's coming down. This is the supply to the radiator. This is the return from the radiator, because the hot water is going to stratify at the top. So it rises up, the cold water comes back, all within the same pipe. Just imagine what is possible, or what could happen when you add a circulator to this job. Anything could happen, right? This is the Eureka Fitting, another one of these inventions that preceded what came to be called the Diverter Tee or the monoflow tee or the Venturi tee. So this is the return side, this is the flow side, and you can see this cuff built in here to drive the water up. And when you see this in real life, it looks like this. This was posted on heatinghelp.com. On the wall, our very popular bulletin board, and the guy put it up there and he says, we just took the asbestos off the job and we've got this. And what is this? what does it do, and what the heck happens if we take it out? So this was a smart person asking these key questions, because if you just arbitrarily take this thing out, the system may never work again. But we said, okay, what you have there is a Eureka Fitting, and this is how it works. And if you go into the Heating Museum part of heatinghelp.com, you'll actually find the original specs for this thing and patent drawings. And if you got a question about anything old and weird, bring it to heatinghelp.com and you're going to get answers there. So don't guess. Mark Honeywell in 1909, and yes, this is the same Mr. Honeywell that gave us that big company, but Mark Honeywell was a plumber from Florida who began inventing things at the turn of the century, and he was absolutely brilliant in the things he was able to put together. But he was faced with gravity systems where this radiator would heat hot before that radiator and so on down the line. So he wanted to make even heat throughout a building without doing a lot of complicated stuff. So what he gave us was this patented fitting in 1909, and I'll show you a close-up of this now. What he's got here is a supply fitting and a return fitting, which is identical, but it's got this kind of a cuff built within on the inside of it. You see that? Goes around like this. So this is going to take the hot water, which will enter and stratify. The hot water will be at the top, and it's got to work its way down all the way until the pipe is completely filled top to bottom with hot water. Then and only then will the hot water crawl under this cuff and come up here and enter the radiator. And when it does, the colder water on the other side will come down and work its way into the cuff and move. So Mark Honeywell, 1909, gives us this brilliant way of making all the radiators in a gravity hot water heating system get hot at the same time. Very smart fella. Time goes by and we begin to see the development of one-pipe hot water heating. This is because back then, the hot water people, particularly Mark Honeywell, were competing with the steam people. And this was actually two separate industries. You had the steam fitters and you had the hot water men. And they would, the steam fitters would say, our stuff is cheaper, it's easier to install, which was all true. And the hot water people would say, yeah, but it also blows up your building, which was also true, because back then they were blowing up buildings at the rate of one every 36 hours. Somewhere in America, a building blew up with a boiler explosion every day and a half. So the steam people had a dangerous thing to sell, and the hot water people had something very safe, but it was expensive because you had two pipes to every radiator, and the pipes had to be large and they had to be the same size. So there was a lot more piping. They were limited to 180 degree water. If they went any hotter than that, it was liable to boil. So the temperature of the radiator was less, so the radiator had to be larger than the steam radiators that went in by the steam fitters. So much more expensive, but safer. So we try to come up with a way that we can have one pipe hot water heating, and that brings us to this invention. This was devised by a man named Oliver Schlemmer, and he was out of Cincinnati, Ohio. And he says, let's on this particular configuration send all the hot water up to the top, kind of like what John Mills did with his Mills system on the steam end of things. But we'll first send all the hot water up to the high point of the system. There's going to be an expansion tank there in the attic, and then we're going to downfeed as the cold water falls. The hot water will work its way down, following the cold water. And now you've got the beginning of modern hot water heat, because here we've got two connections off of one pipe. So we begin to see this idea of diverting water based on delta P, difference in pressure, from one side to the other. Oliver Schlemmer. And he calls this special T that he makes the OS fitting. And this is in 1898. So Oliver Schlemmer gives us this, and this is the OS fitting. Begins to change the industry as we know it. Here's a close-up of it. I want you to just visualize. Imagine you're coming in from the bottom, because that's the way the arrows are pointing in this case. And think, instead of water, make believe you're driving on the road, and this is a road, and it's a highway, and all of a sudden there's this jackknife tractor trailer laying across two of the three lanes. Well, some of the water is going to wait because it gets slowed down. It's going to continue on that main road, creep along and get around the jackknife tractor trailer and go on. But some of the water over here, it's smarter, and it knows, these are the local people. They know that there's a service road that goes around. They can get off the highway and get back on the other side. So if we look here, imagine you're coming up from the bottom. Some of that water is going to go through the radiator and come out the other side. That's the service road. And other parts of the traffic flow here in the water is going to stay here and just keep going straight. So we're really talking about the difference in pressure between this point and this point versus this point over here and this point over here. So wherever the path of least resistance is, that's where the water will flow. And Oliver Schlummer set it up with these special fittings so that the water would generally favor the radiator if confronted with two of these obstructions laying in the middle of the road. And then if we wanted to meter the flow of heat to the radiator, all we have to do is kind of jackknife another tractor trailer, which we call a valve. We partly close that, and that increases the resistance to flow along here, which sends the water bypassing the radiator. So within Oliver Schlummer's 1898 fitting, 1899, when he starts to sell this stuff out of Cincinnati, Ohio, we see all the stuff that comes later. Primary, secondary pumping, all these different things. One-pipe steam, monoflow tees, not one-pipe steam, one-pipe systems, and two-pipe systems. It all begins to flow out of these ideas of Mr. Honeywell and Mr. Schlummer back at the turn of the century. Mark Honeywell also gave us the heat generator, which was a way to compete with the steam people. Because again, the steam people, they would run systems up to 60 pounds in some cases and have very high temperature going to radiator. And the hot water people were limited to 180 degrees. So Mark Honeywell figures out a way to separate the water that's in the open expansion tank in the attic from the water that's in the system by using this device that he called the heat generator. And that's going to allow him to have 250 degree water as liquid, not as steam, in the heating system and still be open to the atmosphere. So how would you do that? How do you keep the water from boiling? Well, that's where the heat generator comes in. This guy was just brilliant at what he did. Now, I found out about the heat generator by mistake. I was working with a friend of mine, Dave Nelson was his name. Dave's no longer with us, but Dave was a good heating guy, and he worked on the North Shore of Long Island on all these Gold Coast mansions that had big steam systems and gravity hot water heat. And he called me up one day and he said, Dan, I'm looking at this thing called a Honeywell heat generator that's next to this boiler. We changed the boiler, but I'm not sure what to do with this. And I'm looking at it on the top. It says Honeywell #1. He says, and I know they had to start somewhere with their numbering system, but it looks like I found the granddaddy of them all. So I said, well, hang on, Dave. Just wait. I'll come over and take a look at it, and we'll see if we could figure it out together. So I go meet him on the job, and there it is, the Honeywell heat generator piped into this main hot water line that went into the side of the heat generator. And then we traced this pipe here, and it went all the way up into the expansion tank, which was in the attic. And Dave at this point disconnects this thing, and he picks it up, and he's shaking it, and he says it's full of something. It must be full of dirt. It's connected to the top of the system. The system's open to the atmosphere. There's a lot of corrosion going on here over the past 100 years. The corrosion probably settles down into this thing. It must be some kind of a dirt collector or some kind of a strainer. So while he's talking, I said, but Dave, if that's the case, why would they call it a heat generator? And as I said those words, Dave tips this thing over. And out of the side of this thing pours about a pint of pure mercury. And the mercury hits the floor and does what mercury will do once it hits the floor. And Dave looks at me and I look at him, and you could have put a grapefruit in either one of our mouths. And it was only then that we go back and we find out, by doing a little more research, finding some more older books, what the Honeywell heat generator was. And this is what it did. So there's the mercury. There's a lot of mercury inside this thing. And there's a pipe within the pipe. So this goes up to the expansion tank here up in the attic. This is connected to the system, but the water in the system is isolated from the water in the tank by this dip tube that goes down into the mercury. So when the water in the system begins to heat and expand, it pushes down on this mercury. The water here pushes down on the mercury, and it causes the mercury to rise up this interior tube. So the mercury is going up and down, kind of like the diaphragm on a compression tank goes in and out as the water heats and expands. So that's how he's able to have 250 degree water at 15 psi pressure in a liquid form and still have the system open to the atmosphere. And the safety of it was that should the pressure get too high, well then the water would have access to this internal pipe, and it would go up here and safely relieve itself to the attic expansion tank. So Honeywell now gives us a system that could work with one pipe to the radiators. It could work with much smaller radiators because his hot water is 250 degrees. It could work with much smaller pipes because the hotter water is going to move a lot faster without benefit of a circulator. And that's why they called it the heat generator. And upon this rock, he built his church. This was a device that put Honeywell on the map nationwide, the Honeywell heat generator. When you see it on a job, it looks like that. And it's a scary thing. And the only moving part in there is the mercury. So if you encounter one, just be aware of what's in there. And when Dave and I had our spill, it was at the time before mercury was declared to be carcinogenic. So we just kind of scooped it up best as we could. But I've since contacted the government and asked them, can we just dump this stuff? I mean, not the mercury, but the water that's been in contact with the mercury for all these years. Can you just drain the system? And they said, yeah, you can drain the system. It won't absorb the mercury, but you have to properly dispose of the mercury. So make sure you do that, because mercury is a dangerous substance. Don't want to leave that hanging around the house. 1915, we start to see the tank move out of the attic and down to the basement for the first time. And here it's working with a heat generator. But the reason why they moved the tanks out of the attic in 1915 is because the tanks in the attic were beginning to freeze. So keep in mind that hot water heat is not that old. I mean, it really just begins toward the end of the 19th century. And by 1915, we realized the benefit of having the tank in the basement. So this is our first closed compression tank, not with a diaphragm. It's got an air cushion in there. And they figure out, well, let me just hook it into the hot water pipe here, the supply pipe going up, and that should be good. And then they put air in the tank and water, and it's about 2/3 water, 1/3 air. And as time goes by, they quickly realize that the tank is going to waterlog all the time. We're going to lose the air cushion. And it takes them years to figure that out, why that is. It takes them about 20 years to figure it out. But what was happening here was hot water would rise up this pipe and enter the tank, and cold water that was in the tank would pass the hot water coming down. So the hot water and the cold water would pass each other in that line going up into the tank. Since there's air in the tank and water in the tank, the air would get absorbed into the water as the water cooled. So when they first fill it up, air goes into the water that's called Henry's Law. William Henry was a fellow I'll tell you more about later, but he was the guy that first said that gases will dissolve in liquid in proportion to pressure and temperature. So when water cools down, it absorbs air. That's why ice cubes have bubbles in them. And when water gets warm, the air comes out of solution. That's why if you leave a glass of water out on the table overnight, it's going to form bubbles on the inside edge of the glass. That's Henry's Law at work. So Bell & Gossett years later comes up with a device called an air troll tank fitting that prevents this gravity circulation between the system and the tank, and that keeps the tank from losing its air cushion. And I'll show you more of that later on. Honeywell, not to be outdone by Oliver Schlemmer with his one pipe, gives us the unique valve. And the unique valve was indeed unique in that it had this Y pattern inside of it. And the Y pattern gate would allow water to flow into the radiator. And there's just this baffle that sticks inside the radiator. So the water would flow into the radiator and come back out through the same side. And if you didn't want heat, you just move the Y pattern, quarter turn. And the water would now bypass the radiator and go on to the next online. This is what you see in the real world. So there's the Honeywell unique valve, the supply, the return. And this is a gorgeous old radiator. Notice that they put the air vent up here. Because, again, it's gravity hot water heat, so the radiator vent could be on either side. It really didn't matter. The air is going to rise to the top, and you could vent it over here, vent it over there. It didn't matter. This picture was posted on our website by a homeowner who just bought this house and wanted to know what the heck this thing was. So there's the Honeywell unique valve, and notice here, in this case, the air vent is way out on the end. And the guy told us that with that little baffle that only goes in about just past the first section, when he gives that a quarter turn, the radiator very, very quickly heats. So gravity hot water heat will move very quickly through a radiator if the piping is all right. So it doesn't take long to get this radiator hot, even though it's as big as it is. And again, if you ever see something you don't know what it is, just take a picture of it like this guy did, bring it to heatinghelp.com, post it on the wall, and somebody's going to answer you within minutes and tell you exactly what it is you're looking at. And the site probably also has the literature for that product. Which brings me to this. This is not the house that I visited years ago, but it is like the house I visited. And I've got a story for you here about replacing boilers on hot water heating systems. Now, in the interest of saving fuel. So this was in a town in New Jersey called Upper Montclair, which is one of the wealthiest communities in America. And I was doing a seminar in New Jersey, and a fella came up to me at a break, and he says, I'm just a homeowner, and I'm wondering if I could hire you as a consultant. I was doing that sort of work at the time. And could you come and take a look at my house? I just bought it, and the fuel bills are just astronomical. And I said, well, where is the house? He says, well, it's in Upper Montclair, New Jersey. It's a big house. So right away, I'm thinking dollars. Right? I'm thinking he's a rich guy who's miserable. So I should go look at this system for him. So I get there, and this wasn't the house, but the house was just very much like this. And I get there, and there's an oil truck making a delivery, and it wasn't your standard size oil truck. It was a really, really big oil truck. And there was a guy with a hose that was the size of my thigh. It was connected to the truck, and he's got it plugged into the house, and he's whistling. And the homeowner says to me, that guy's here every 10 days. Every 10 days he's making a delivery to me. He says, I don't know how I could afford it. I said, you could afford a house like this, but you can't afford to heat it. He says, it looks like that. He says, I want to just get all my options. What can I do to get these fuel bills down? So I said, well, let's go inside and take a look, see what you got. So we go in the house. He says, well, where do you want to start? And I want to see everything because I'm just nosy and love poking around rich people's houses. But I said, well, let's start in the basement. And we walk down the basement and we make this turn. And my leg's actually locked because I look up and I see this house has 8-inch screwed pipe. Now, if you've never seen this before, it's bigger than 8-inch. So if you look at an 8-inch screwed T, it's massive. And you just think about like, who lifted that and caught us right on it back in the day? This must have been like Popeye and Bluto working on this job. Like, who was able to do this? Who are these people? So I'm looking at that, and he says, well, why so interested in the pipe? And I explained to him the beauty of this, and of the work, of the skills that these people had. And I'm showing him how this pipe goes to the first floor because it comes off at a 45-degree angle, and this pipe goes to the second or third floor. So he's interested in that, but he says, do you want to see the boilers? And I said, boilers? He says, yes, there are 2 of them. So I said, by all means. So he takes me into the boiler room, and I'm looking, and then once again, my legs stop moving because I'm looking at 2 ideal red flash boilers, each rated at 1/2 million BTUs. Now, this is in a guy's house. So Ideal was a trademark of the American Radiator Company, who was the big deal boiler company at the turn of the century. They became American Standard. But if you've never seen an Ideal red flash boiler of the 1/2 million BTU variety, this thing is like the size of a minivan. And it used to burn coal, and at some point they had removed the grates from the bottom of it, and they filled the bottom with sand, and they hung oil burners that were as big as the 4th of July on each of these, and they were just vomiting fire into the bowels of these boilers, and they were both connected to that truck outside. So the guy says these things never shut off. They're just doing this. And I said, this is crazy. An Ideal red flash boiler it's got these massive doors on the side. And you can open one of those and look inside. You could yodel in this thing. It's so big and massive. In fact, you could cremate your spouse in there. Nobody would ever know. You get a number 10 smoke for a few minutes. Other than that, nobody would ever know that you did that. So I'm just getting such a big kick out of this. And the draft of these things was incredible. So I said to him, has anybody done a heat loss calculation on the whole house? And he says, well, what do you mean? I said, well, to size the replacement boilers if you're going to have these replaced, which you really should. So he says, well, the oil company sent a guy and he sized the boiler that I would need. So I said, did he go upstairs and measure your windows and your doors and your rooms and everything? He says, no, he told me that wasn't necessary. These boilers have been here for years, so they must be right. And he wrote down what was on each boiler. Here, I'll show you. And he shows me the proposal. And he says the guy wrote down 1/2 million BTUs plus 1/2 million BTUs. That's what's there now. And then he gives him a quote on a single boiler, telling him that it's crazy to have 2 boilers because it's twice as many things to break down. Why would you want to have 2? So he gives him a proposal for a single boiler rated at 1,300,000 BTUs. The thinking being it's an old building. It never hurts to have a little bit extra. So I said to the homeowner, well, let's put that aside because this guy may be looking at this as a vending machine. So let's go do a heat loss calculation. So we go through the whole place, and I take them through, and I've got a heat loss program, and I figure the heat loss for the whole building, and it turns out to be 375,000 BTUs. Now that's massive because the heat loss of my house is like 40,000 BTUs. So this is like 10 times my house. But right away, this tells me, since I had 2 1/2 million BTU boilers, that one of those boilers was a standby. It was never supposed to be firing unless the other boiler was off. It was put in by rich people who decided they never wanted to be inconvenienced. I'm all for that. And why should they not have two boilers if they could afford it? So, even the one boiler was oversized. So right off the bat, the homeowner says, these guys, they're out of here. They're done. This guy was trying to cheat me. So I thought a lot about, what human quality was it that cost that company, not just the boiler business, but the oil business. And it dawned on me, the more I thought about it, it was pretty much probably cynicism. I think the salesman that came out was thinking that if I spend the time doing a heat loss project on this mansion, the guy might not give me the job, and then I'm going to have wasted my time. So let me just quote him what's on here, and that's good for me too, because we're going to get the oil account. So he loses. He loses completely on the whole thing. When you do a heat loss calculation on any hot water heating job, if you're competing with other contractors that don't do heat loss calculations, you will consistently come up with boilers that are smaller than the other guy is quoting. Then all you need is the courage to say, I believe in my numbers. Because they're going to tell the homeowner that you're wrong, that the boiler is too small. And I once met a contractor who said, I'll quote on the smaller boiler and give them in writing a promise that if this doesn't heat your house, I'll take it out and put in what the other guy was going to put in. He says, I've never had to do that. He says, and my closing rate is tremendous. So I said to the homeowner, we're going to size two properly sized boilers, because it does make sense to have two boilers, because it doesn't get that cold every day. And like you've got a lot of clothing, but you don't wear it all on the same day. You wait till it gets really cold to put on sweaters and jackets and hats and gloves and boots. So wouldn't it be nice on a milder day if you could shed some of your boiler so that you're not wasting that much fuel? So I said, we're going to put in two properly sized boilers, each half of 375,000 BTUs. He said, all right. I said, here's how we're going to do it. You got these 8-inch pipes. There's two going out of the boilers out into the building, and there's two coming back. We're going to tie all those together, and we're going to do that with 2-inch copper. We could do this. And then I said to him, I want you to go down to the supply house and tell the counterman you need 4 8-inch screwed by 2-inch sweat reducers. I said, now he's going to try to jerk you around because you're a homeowner, but don't take no for an answer. Well, are you laughing? Good, I hope so. I was laughing too. I was just kidding the guy. We used flanges to do it, or his contractor did anyway. And in this line, we put a circulator that was high flow, low head. So at the time, we used a Bell & Gossett Series 100, which was the right circulator for this. That was the classic circulator when converting gravity hot water heat. So it could also be something like a Taco 0010 that has a similar pump performance curve. So you're trying to move a lot of water against very little resistance to flow, because when the water's in this big pipe, it thinks it's in the ocean. There's hardly any resistance at all out here. So we flow through here. I said to him, now what we're going to do is we're going to connect the two boilers. This is what I want your contractor to do. We're going to do something called primary-secondary pumping. So this is the primary pump, and that's going to come on whenever it gets below a certain temperature outside. We used a control from Techmar to turn the system on when it got cold outside. It turns on the primary circulator. It's like a big merry-go-round. The water just keeps flowing around. We could do that because there's no check valves in this system. And then I put 2 T's that are closely spaced together. This is going to be secondary piping. And we come down into a manifold. So we go into two circulators here, one for this boiler with a check valve, and the other for this boiler with a check valve. And the idea is that on a mild day, this primary circulator comes on, and the burner comes on in one boiler, say it's this one over here, and this circulator. So this circulator sips some of the water out of the primary flow into the secondary, through the boiler, and back to the system. Now, because we were doing this at a time before condensing boilers became popular, I also included a bypass so we could take some of the hot water and blend it in with the water that's coming out of the primary main to bring the temperature going back to the boiler above 140 degrees, because that was the lowest temperature that this boiler was able to take. So these are bypass lines to bring the temperature of the return up to something higher than 140 degrees. The check valves are there because without them, if the primary is on, you're liable to get this. It'll come out of here and it would go this way, backwards to the off boiler, and you'd be circulating through here. So the check valves prevent that from happening. So for most of the days, when it's not the coldest day of the year, one boiler will do, and on a very cold day, the second boiler will come on and it will raise the temperature up to whatever we need out here, say 180 degrees. So they did this, and I tracked this job through the following winter, and for most of the winter he just ran one of those boilers instead of what the oil company was proposing, which was a single boiler of 1,300,000 BTUs. There's a big lesson to be learned there, not just in the mechanics of all this, but in what it takes to get the job by not being cynical, lazy, complacent, whatever it was he was. And speaking of pumps, gravity hot water heat was great, but as it got older, since it was open to the atmosphere, you had a lot of corrosion going on in the system. So the system began to corrode, and you get all these nooks and crannies on the inside of the pipe, and something had to be done. We had to have an improvement. So we get the circulator, which shows up in 1923, and it's invented simultaneously in America and also in Europe, in Germany. In Germany, it's invented by a company that comes to be called Wilo, W-I-L-O. And in America, it's invented by a man named Homer Thrush, who would work with Mark Honeywell from time to time. So Homer Thrush gives us the first circulator, and it's a vertical inline circulator, so the motor sits above the pump body, and he had big flanges on it because it was designed to go onto a gravity hot water heating system on the return side for a couple of reasons. First of all, the water was cooler on the return side, and that was better for this pump. And second of all, Homer Thrush's original circulator had a packing gland, not a mechanical seal. So the packing gland had to drip all the time, and it had to be near a floor drain. So it became normal to install the Thrush circulator on the return side, pumping back from the system and into the boiler. And by doing this, they sped up the way the water was moving, and it added years of service to the gravity hot water heating system, which had been corroding. So a little bit of time goes by, and a company out of Chicago called Bell & Gossett is in business, and they're selling just a side-arm heater for coal-fired boilers. And it's called an Excelso Heater, and it was just an iron shell, and it had a copper tube in it, and it too worked by gravity just to heat hot water. Taco in Rhode Island was doing a similar thing, selling a similar product. In fact, Taco stands for the Thermal Appliance Company, and it comes from that original idea of having a sidearm heater to heat hot water. So both of these companies start looking at this idea of what Homer Thrush was doing, and Bell & Gossett first comes up with this idea of what they call a booster, which they trademarked as a name. It was quite clever. That was done by a man named Ed Moore, who was their marketing guy. And because they called it a booster, it said what the thing was going to do. It was going to boost the heat in an old gravity hot water heating system. And it was designed, again, to pump down into the boiler because that's where the water was coolest. You see, but this pump from Bell & Gossett had a mechanical seal here. It didn't need a packing gland. It worked on a mechanical seal. So it didn't have to be near a floor drain. It also didn't have to be set for so many drips per minute. So it was more trouble-free. It did need to be oiled here and on the motor. But it was a lot better than what Thrush was offering, so it became very popular. And they put this on the return side for the main reason that the water was coolest there, because their mechanical seal was made from a material called carbon and another material called remite. So you've got this carbon ring that's spinning on this very hard material called remite, but the remite could not take very hot temperature. So the B&G people figured that if they put the circulator on the return, it would be better for the mechanical seal, and that's the only reason why it wound up there. Fast forward a couple of decades, and now we're into the 1960s, and John F. Kennedy gets elected president, and he declares because of the Soviets and the Cold War, we're going to put a man on the moon before the end of the decade and bring him back safely. And this forms NASA, and NASA tries to figure out how we're going to do this, and we have the Gemini space program begins, and all this stuff actually has an effect on circulators, because to make space capsules come back to the atmosphere, you've got to have some material that can take very high temperature. And they begin to look to companies that could develop ceramics that could take high temperatures. And the company that stands out above all others with this, believe it or not, is Coors, the Colorado Brewing Company. Coors made all the ceramic tiles for the space shuttle. So this was a company that was prominent in this, and we begin to see these ceramic tiles coming out, and ceramic is very good for mechanical seals as well. So before long, the people that make mechanical seals said, let's get rid of the remite and replace it with ceramic. So as soon as that's done in the early 60s, we now have circulators that could take 225 degrees Fahrenheit continuously and 250 degrees intermittently. So that's way beyond the range of any temperatures that we're using. I mean, we usually go up to 180 and that's it. So from the very early 1960s on, there is no reason anymore for this circulator to be mounted on the return side of the system, other than it's a habit. And it's a habit that people accept. And also, with the building boom that takes place in the 1950s, we begin to see the development of packaged boilers. The packaged boiler has the controls attached to it and the circulator as well. And the nice thing about that, if you're a contractor, is it's easier to install because everything is all put together. And the boiler manufacturers are getting a great deal on these circulators because the people that make the circulators almost give them away to the boiler manufacturers, figuring that down the road, when the circulator fails as time goes by, and it'll probably fail many times, it's going to be replaced with the same circulator. So they want to get in there first. It's kind of like selling razors. You know, you don't make the money on the razor, but you're going to make it on the blades. Or you don't make the money on the printer, but you're going to make it on the ink. So the circulator manufacturers give the boiler people this great price, and you start to see the circulators getting installed. And they're all installed on the return side because it makes the packaging easier. If the circulator's down at the bottom, the box can be shorter. You can get more of them stacked in a warehouse. You can get more of them on a truck. So again, habit and packaging kick in, and this is why circulators are on the return. But from this point on, there's really no reason to have them there. Now, another thing's taking place at the same time. On a larger scale, we have working in the engineering field, or engineers that are doing big apartment buildings now after World War II. There's a huge building boom in the 1950s, and they stopped using steam in favor of hot water. So you start to see this big move in hot water, and you also see the great use of what we call these diverter tees, or what Bell and Gossett called the monoflow tee, or Takeo called the Venturi tee, because that allows for a less expensive installation, which is comparable to one pipe steam. So you got one pipe diverting water through a radiator. But when you go into really big buildings with that system, you find that the pressure drop through the tees is cumulative because all the water is flowing through all the tees. So you wind up with some pretty big pumps that have to move the water through all these monoflow tees or all these Venturi tees throughout the system. And naturally, the engineers, going by habit, were specifying these really big pumps to be installed on the return side of the system where the water was coolest, even though there was no reason to do that anymore because we now had this ceramic mechanical seal. So a few years go by and they begin to see massive boiler failures. And the failures are being caused by oxygen corrosion. Something is letting air into these systems and it's just eating the iron and the seal in these boilers. So nobody understands what's going on until a man named Gil Carlson comes along. And Gil Carlson was my teacher when I was growing up through the rep agency. We represented Bell and Gossett at the time. And Gil Carlson was the guy that taught me hydronics. And he writes this very famous paper for ASHRAE, which is the American Society of Heating and Refrigeration Engineers, and Heating, Refrigeration, Air Conditioning Engineers. And ASHRAE is as close to science as we get in the heating industry. And Gil writes this paper where he explains that these high head pumps that are producing a lot of pressure, mounted on the return side of the system, pumping toward the boiler, are causing a drop in pressure that's sucking air into the system, and that is the air that is eating the boilers, and that air is then getting spit out of the system by air separators on the supply side. So the whole engineering community worldwide pretty much goes, aha, and they realize that he's right, and they move the circulators to the supply side, pumping away from the compression tanks, not so much from the boiler, but the compression tanks, and I'll tell you a lot more about this as we go along. This knowledge never really filters down into the packaged boiler business and the residential business and the light commercial business. Contractors keep doing what they're doing. And then this is what leads to problems as we roll into the 1970s and the small, high-speed, water-lubricated circulators show up on those jobs. And to understand why this happens, you got to think about the way an impeller works in a centrifugal pump. Centrifugal pump works by centrifugal force. So it's spinning to the right here, clockwise as you see in a direction. This is the eye, this is the inlet to the impeller, and you're looking at it dead on. It's kind of like the eye of a hurricane. So when it spins, it throws out the water by centrifugal force. You get a low pressure point here in the middle and a high pressure point at the outlet side. And since water is not compressible and the system is completely filled and under pressure, being held there by the compression tank, if you move one drop of water anywhere in the system, it's like moving one link on a bicycle chain. If you move one link, all the links move at the same time. So in a heating system that's closed to the atmosphere, if you move the water through the circulator, everything in the system is going to move. It's like one big Ferris wheel. So knowing that, if you look at the way this thing works, you could see this pickup in speed, the centrifugal force on a gauge as a change in pressure, as a delta P, difference in pressure. So here, for example, if we have a gauge on the suction side that reads 15 psi and on the discharge 25 psi, that means that this circulator is producing a pressure differential of 10 psi. Now 1 psi is equal to 28 inches of water column, or 2.3 feet of pump head. 28 inches or 2.31 feet. So if we take 10 times 2.31, we get 23 feet of head. So now if we wanted to know how much water was flowing with this circulator, we would go on the manufacturer's pump performance curve, which looks like this. It's showing the gallons per minute against what they call total dynamic head, which has nothing to do with the height of the building. This has to do with the resistance to flow as the water moves through the pipe. So it shows you on the curve that as the resistance gets lower on this side, the flow rate will go higher. So if we begin to close valves, that increases the resistance, and the gallons per minute flowing will slow down by moving up this curve. So GPM versus resistance to flow. And if I was looking at that pump curve that we just looked at, or that pump with the 23 feet ahead, if we drew an arrow across here, we're in intersects with the pump curve and then go down, we might find that that pump's moving 100 gallons per minute. Now, as we begin to throttle that by closing valves, it'll move up this way, and now you'll see that the head increases dramatically, but the flow rate slows down as well. So as we throttle down on a circulator, it builds pressure. That's on a single speed circulator. And this is often why you'll have zone valves that bang, or you'll have velocity noise as the water moves too fast through the system. All of this is cured in modern times by smart pumps that have ECM motors on them, because the pump will just automatically find itself anywhere in this slice of pie here. It'll just drift around until it finds exactly what you need, and it'll do that without building pressure. So that's modern times. But this is a single speed circulator. Which brings me to this guy. This is a 2 horsepower high speed circulator, and there was a story behind this, because when I was very young and just starting out working for the manufacturer's rep, they would send me out to help contractors, because I had done a lot of research. I'm not an engineer, but I'm a reader, and I did a lot of reading and a lot of research, and I went out to help this contractor who had this pump, not this exact pump, but it was a different version of that pump. And we're on the job, and he says to me, "This pump's making a lot of noise." He says, "I think we need a new pump." And I said, "Well, maybe it's just got the wrong size impeller in it or something, or it's oversized." So he says, "Boy, you really know your stuff." And I was like 24 years old, I think. I think he was like 25 years old. He says, "You sure we don't need a new pump?" I said, "Well, let's try something and we'll find out." So on a pump like this, you got a tapping right here. That's for a gauge. That's on the suction side. And another tapping over here. That's on the discharge side. This tapping is to vent the air out of the volute. This is the volute. The impeller's inside here. The mechanical seal is back here. And it's all motor over here. No coupling. So I put a gauge on there on the job, and I put a gauge on there. But this was in a mechanical room. So follow the sequence of this. He thinks I'm very smart. So I go in there. I shut off the power to the circulator. I turn off the valves to the circulator. I open this port. I put a gauge in there. Another gauge in there. I open the valves and I start the circulator, and it gives me a reading. And I get the differential pressure across the pump, and I take that to a pump curve. And I say to the guy, "This pump is so oversized. That's why it's making noise. It's called velocity noise." So he says, "You mean we don't need a new pump?" I said, "No, I don't think so." I said, "Usually we could just put in a smaller impeller in here, which will cut down on the amount of flow." And I said, "In this case, the pump is so grossly oversized, we could probably just leave the impeller out and just run it on the shaft key." And he says, "You serious?" I said, "No, I'm joking, but thanks for thanks for considering it." So he says, "Boy, you're really smart." He says, "I've got some more questions to ask you." So I said, "Well, okay, let me first get my gauges back, and we'll step outside where it's quieter." So again, follow the sequence. I turned off the motor. I closed the valves. I took my gauges back from these points. I put the ports back, the plugs back in the ports. And I stood up and I started the pump again, and we stepped outside. Now, if you're following closely, you're going to notice that I missed the part about opening the valves. I forgot to open the valves. So we're standing outside this mechanical room for no kidding, what was no more than 7 minutes. And the guy's just basking in my brilliance and asking me all these questions. And I hear behind me inside this room this violent explosion. And he says to me, "What was that?" And in that horrible moment, I knew what it was because I had read about this in a book. But I said to him, "I have no idea," which is exactly what you would have said under the same circumstances. So we open the door, and I look inside the boiler room, and this cast iron volute is gone. It's gone. It's in pieces. It's stuck in a cinder block wall. The impeller is spinning in space. And the guy looks at me, and he says, "Didn't I tell you we needed a new pump?" So I said, "You're right." And I sold him a new pump, which is exactly what you would have done under those circumstances. So I tucked my tail between my legs. I went back to my office, and we had an old engineer that worked for us. He was an old merchant marine guy. His name was Walter Bosch. And Walter was a guy who was comical because he could not get through a sentence without dropping the F-bomb. I mean, this guy was an old sailor, and he cursed better than anybody I've ever heard in my life, and he chewed me a new one. It was when I told him what I did. And he says to me, "Don't you realize the amount of heat energy that gets built up when you run a circulator with the valves closed?" I said, "Well, I do now. It was enough to make cast iron explode." He says, "Yeah." He says, "Let me show you a formula that I got at a seminar I went to years ago that was being taught by a pump expert. And this is the formula that shows the temperature rise in degrees Fahrenheit per minute. And all you got to do is figure out this is a standard 5.1 factor times the brake horsepower, which is where on a pump curve it shows where the pump curve reaches 0 GPM. That's the brake horsepower at shut off. And into that you divide the amount of water that's inside the pump, the volute volume in gallons, times the specific gravity and the specific heat of the fluid. In this case it was water. So we went through this, and he gave me an example, and he said, if I had a 40 horsepower pump with 200 feet of 3-inch pipe attached to it, and I ran it, with all that water, and just ran it with one valve closed where the water couldn't actually move, he says, I would see a temperature rise of 590 degrees in 8 hours. He says that would cause the paint to melt on the pump. He says, now, young man, the pump that you just blew up is a 2 horsepower end suction high-speed pump. He says, when you run that with the valves closed, you're going to experience a 1,590 degree Fahrenheit rise in 1 hour. So within 7 minutes, you could see how high we got. It was hot enough to make the pump blow up. So I learned a lesson, and I never did that again, and I never closed the valves on a pump again while it was running. And I encourage you to feel the same way about this. And if you ever have to throttle a pump that's oversized, by all means use a throttling valve, but on the discharge of the pump. Never throttle the suction side, because if you throttle the suction side, you're going to get a phenomenon called cavitation. This is what happens when the circulator tries to throw out more than it can pull in. So what happens then is the pressure here at the eye drops so severely that you'll get vapor. It's not steam, because we're not adding BTUs to it. All the valves are open. We're not heating the water. It is actual vapor that forms because the water can't stay liquid. It's actually in a vacuum. So you get a vapor bubble that forms and gets thrown out to the outer edge where the pressure is high. So suddenly this vapor bubble that formed here collapses out here. And so it's water that suddenly leaves a hole in the water. And the hole is filled with other water. And the water comes in at astonishing speeds and smashes into the edges of the impeller and just destroys the impeller. And that's called cavitation. And it looks like this in real life. So this is supposed to be solid out to the edge here. All of this was eaten up by cavitation. And in real life, it sounds like you're pumping gravel. And if you want to hear this in real life, just if you have a swimming pool, or better yet, if your neighbor has a swimming pool, go over to the pool skimmer there and take a beach ball and just stuff it in while the filter pump is running, and listen to what happens. Because the filter pump is going to immediately begin to cavitate as it throws out more than it can suck in. And if you're lucky, you'll even see the hose going to the suction side collapse as it goes into vacuum. So don't do that on your own house. Do it on your neighbor's. So when we talk about pump head, we're not talking about the height, because like a Ferris wheel, the weight of the car going up over here is balanced by the weight of the car coming down over here. In a hot water heating system, we use a fill valve to fill the system completely to the top and put it under a few pounds of pressure. So there's no lifting involved, because the weight of the water going up is balanced by the weight of the water coming down. So when a circulator comes on, it's very much like the motor on a Ferris wheel in that it's not doing any lifting at all. It's just turning this big wheel of water. And that's how we heat the building. So when we say pump head, we're not talking about height. We're not talking about the size of the building. If you had a 10-story building and you put in a circulator and then you laid the building on its side, it would use the same exact circulator because the piping hasn't changed. So with that in mind, let's talk about the circulator's relationship to this compression tank and go back to that discovery that Gil Carlson made when all those boilers were dissolving through oxygen corrosion. I want you to imagine that we've got a loop of piping and a compression tank with 12 pounds of air pressure on this side of it, and a circulator. So we're going to remove the boiler. We're going to take out everything extraneous because I just want you to focus on the relationship between this circulator and this tank. We filled it with exactly 10 gallons of water. It's sealed to the atmosphere. Nothing else can get in, nothing else can get out. So we've got 10 gallons of water in the pipe, in the pump, and in the tank. When the circulator comes on, it's going to throw out what's at the side of itself, and that's going to make this big wheel of water turn like that. And everything is going to move at the same instant. There's no lead lag here. It's like moving one link on a bicycle chain. You move one link, the whole chain moves at the same time. So the question then becomes, when this water is moving around, can any of this water enter this tank? When the circulator comes on, can it push water into the tank? Now think about that for a minute, because I know you're probably thinking that that's possible. You're probably thinking that the force of the pump is going to shove water into the tank. But while you're thinking about that, I want you to remember that we've only got 10 gallons of water to work with. And if we take any water out of this pipe and add it to the tank, we're going to be left with a hole where the water used to be. And since water is not stretchable like taffy, there's nothing that's going to fill in that hole. So we could say, in terms of real-world physics, that when a circulator and a hydronic system operates, it is impossible for that circulator to put a drop of water into that tank, because that would leave behind a pure vacuum, which can't happen. So the circulator runs, no water goes into that tank. Now, let's move the circulator over here so that we're pumping away from this point. And again, it's the exact same system, 10 gallons of water. When the circulator runs, it's going to make the big wheel of water turn like that, just like a Ferris wheel. And the question then is, as the water is moving, can it draw by a Venturi action water out of the tank to enter this flow? And if you think about that for a minute, you may like the idea that water is going to suck out of the tank and up into the flow. But then once you start to think a little bit more, you realize that water is not compressible. So if the pipe is completely filled with water when we start out, we can't take any water out of the tank. There's no place to put it. The pipe is already full. Well, you can't squeeze water. It's not compressible. So we could say with great assurance that when a circulator runs, it cannot remove a drop of water from that tank. So it can't put water into the tank, and it can't take water out of the tank. And because of this, Gil Carlson back in the 60s called the tank the point of no pressure change. This was a major breakthrough in the science of hydronic heating. He said that the circulator will respond to the point of no pressure change. This is like a hydronic bookmark. This will never vary. If we fill it at 12 pounds, unless we heat the water, if we heat the water, it's going to expand and squeeze the air cushion. But if we don't heat the water, if we're just looking at the circulator, the pressure here will be a continuous whatever we set it at, in this case 12 pounds. So if I pump away from it, the circulator is going to add its differential pressure to the 12 pounds. But if I pump toward it, the circulator is going to subtract its differential pressure from this, because it can't make the pressure here any greater than 12 pounds. So this is in charge. The tank is in charge, not the circulator when it comes to what the pressures are going to do. So here's an example of that. Let's say the point of no pressure change, PONPC, is 12 pounds right here. And I'm going to use a little circulator here, something like you'd have in your house. This is a small water lubricated circulator, and when you have that, it produces about 6 pounds of differential pressure. So this will always stay at 12. So this is 6 plus 12. There'll be 18 pounds of pressure here, and the water will flow around the big wheel, like moving a Ferris wheel. Now, let's move the circulator over here so that it's seeing half of the system pressure drop on its supply side and the other half of the system pressure drop on its return side. Let's see what happens. Now, we're going to see the same 6 psi differential, but it's going to be split in half. Instead of going up to 18, we only go up by 3 to 15. And instead of staying at 12, we drop to 9, which represents the 3 psi pressure drop along this run. Got it? Okay. Now let's move it back here so we're pumping directly at the point of no pressure change, which can never be any more than 12. Move the circulator to there. It comes on. This stays at 12. It produces a 6 psi differential by dropping its suction pressure by 6. So now the circulator comes on. Consider this for a minute. We just removed half the system pressure. It's gone. What used to be 12 is now 6. And that's down in the basement where the boiler is. Imagine what's going on the top floor radiators that may have some air bubbles in them. If you remove this pressure, suddenly the pressure on the air bubbles also drops. So the air bubbles, when you remove pressure, the bubbles get bigger. Right? That's Boyle's law. You remove pressure on a gas, it's going to get bigger. You add pressure to a gas, it's going to get smaller. So this was what was causing the corrosion of the boilers back in the 60s, and the engineers realized it, and they moved those big pumps to the supply side. But it never really caught on until recent years in the minds of the people that do residential work and like commercial work. But this is what's causing your air problems. So here's an example in a long, low warehouse. We've got a ceiling-mounted tank here. There's the boiler. And in this case, we're going to put a circulator here. And this is like a 2 horsepower inline circulator. And let's say that circulator can produce 13 psi differential pressure, or about 30 feet of pump head. Now when it comes on, if I'm filling the system here with 12 pounds of pressure at the point of no pressure change, which is where the tank connects to the boiler, 12 psi plus 13 psi is going to give me 25 psi. And that's what you'll see here when this circulator comes on and runs. And everything's fine. The big wheel of water will turn. You got a positive pressure. All's good. Now let's move this circulator down here and see what happens. I'm going to put it down here, pumping right at that point of no pressure change. Now the point of no pressure change is still the same. It's still 12. And the circulator hasn't changed. It's still producing 13 psi differential pressure. But watch what happens when the circulator's ability to produce pressure exceeds the system fill pressure. Suddenly we have a case of 12 minus 13, which is minus 1 psi. And that's equivalent to 2 inches of mercury vacuum. And that's what you'll have inside that pipe when the circulator runs. So what's going to happen immediately is the mechanical seal is going to start to suck air in through itself. And also, if this is a high point and somebody installs an automatic air vent there, well, air is going to go into the system right through that automatic air vent because it'll be subatmospheric. So air comes flooding through here, hits the boiler, rots the boiler, and gets spit out of an air separator on the supply side. And this was the tragedy that they were facing in the 60s before they moved those circulators to the supply pod, pumping away from the compression tank. Back to a small boiler. Here's a common mistake. The circulator gets installed on a return because of habit, because that's the way my grandfather used to do it for whatever reason. You put it down there, and you're going to bring the fill valve in right to the suction side of the circulator. Because again, it's easy to pipe that way. Up here, we've got the compression tank, the air separator, and the main air vent. So that's point of no pressure change. That's 12 psi. Down over here, we've got a 12-pound feed valve. And over here, you got 6 pounds differential when the circulator comes on. So it comes on, it may increase the pressure by maybe 1 pound as it flows through the boiler before it meets the point of no pressure change. But the balance of this differential pressure is going to show up as a drop in pressure on the suction side over here. So when the circulator runs, suddenly you've got 7 psi here. That's what's inside the system. This is a 12-pound feed valve. So high pressure goes to low pressure. So when the 12 pounds feed valve sees 7 pounds, it will feed. And you might think that it will feed every single time the circulator runs, but that's not the case. It's only going to do this once. It's going to do this on the very first cycle. This drops to 7. This feeds, bringing the overall system pressure up to about 17 or 18 psi. And then it's going to stop. And the next time the circulator starts, it'll drop the pressure down to 12 again. So the feed won't go below 12. It'll stay there. And you think, well, what's the big deal? I'm operating at 18 pounds instead of 12. No big deal. My relief valve is set to pop at 30. That can't hurt me. But you know what? You're wrong. It can hurt you, because when you size a compression tank, one of the things you take into consideration, actually several of the things, you have to know the volume of water in the system in gallons. You have to know the average water temperature that you're going to be operating at, which is probably 170 degrees Fahrenheit. And you also have to know the difference in pressure between the fill valve setting and the relief valve pop-off. So normally it's 12 over here and on the relief valve 30. When you increase the feed valve by 50%, your required compression tank size doubles. So if this was, say, an Amtrol number 15 tank, suddenly you need a 30. The 15 is half the size that you need. So you might start having problems with your relief valve popping because your compression tank suddenly is not big enough, and it's not big enough solely because of where you installed your feed valve. So this is a very common problem. You see it every day in life. There's the feed valve up there. Look where it's going in, right into the suction side of the circulator. So this guy's going to have a problem. He's going to be changing tanks or putting in oversized tanks and wasting money and leaving the profit on the job when it should be in his own pocket. Don't get sucked into that. I wrote a book called Pumping Away years ago, and I wrote it with the contractor in mind because the only one that really benefits from this is the contractor. And the boiler manufacturers got a little upset with me because they were mounting the circulators on the return, and they said, Dan, if we move the circulator to the supply, we've got to change our literature, our packing information, our procedure on the assembly line, and we wouldn't sell any more boilers. I said, well, why don't you just leave the circulator in the box? And they said, no, because then the contractor's going to think, why don't I just buy my own circulator? And we're making a lot of money on the circulator. So it was a human problem. So one boiler company came out with a drawing that said, we're going to put the circulator on the return, as we always did, but to keep in compliance with the laws of physics, install your compression tank on the suction side of the circulator and you'll be fine. And, that was true, because look what happens here. If that's the point of no pressure change, and it's 12 psi, and you're pumping away from that, and your circulator comes on and it can produce 6 psi, you'll see 18 over here. And with a single circulator, this is perfectly acceptable. But we don't use single circulators in most cases. We zone. And if we zone with circulators, we've got this other circulator involved here. So now watch what happens, because one is pumping away from the tank and the other one is pumping toward the tank. So we set up a situation where this happens. This circulator is off and this one is on. Now, when this one is on, it makes 18 pounds of pressure. This stays at 12, and everything's fine. You got flow. Over here, when this guy is off and this guy is on, you might get a slight rise in pressure to reflect the difference in, the pressure drop across this piping here. But the majority of the pressure is going to show up as a drop in pressure over here. And as long as this one is on by itself, this zone will work fine too. But on a really cold day, when all the zones are on, that's when this happens. Both of them are on. This guy is producing 13 psi on its outlet side. This one's producing 18. And keep in mind, I'm leaving out the flow control valves that would be in part of this, which is a check valve. So if this is a check valve with 13 psi trying to open it and 18 psi forcing it closed, you're going to have a situation where there's heat in this zone and no heat in that zone. And when you go out on this troubleshooting call, I guarantee you're going to start bleeding radiators and you're going to start purging lines. And you're not going to see any air. And remember what I taught you earlier. If you don't get any air, it ain't an air problem. So stop the bleeding. So this is a situation that's very easy to avoid if you just move everything to the supply side of the system. So with that in mind, let's take a little break here, and we'll be back and we'll start to talk about different piping systems. So let's take a look at one pipe hydronic systems. There's a bunch of them. This was a fun job. I was on this with my friend Al Levy, who writes for Plumbing Mechanical Magazine. That's Al's hand right there. This is back when he was still in his family's oil and contracting business. And we were on this job in a person's house where Al was there because the boiler had actually dissolved and he was replacing it. Somebody else had done the work before him. But to figure out why they had no heat in this bathroom that was upstairs, he had to tear down the ceiling, and we find this diverter tee and a standard tee. And this piping goes from here all the way upstairs to the bathroom, and then it goes back down to where Al was. So they didn't have any heat up there in the bathroom. So Al and I are looking at this and we're saying, okay, imagine your water. If you were water and you're flowing down this line, would you go from here to here, even though there's a diverter tee in there, or would you choose to go up this pipe all the way up to the second floor and then all the way back down to this tee? What would you do if you were the water? And the answer was pretty clear. We'd stay in the pipe. So that was a problem. Where there is no flow, there is no heat. So if there's no water flowing up to the radiator, obviously there's going to be a cold bathroom. So the guy that was there before Al told a woman that he'd come back and bleed the radiator, which he did again and again and again. but each time he bled it, the radiator would get hot because he's not actually bleeding the radiator, he's draining the system through the radiator. But then when he left, it would get cold again, and also while he's bleeding, he's not getting any air. So once again, if I don't get any air, it ain't an air problem. So I really should stop bleeding at that point. But this guy was persistent, so he got to a point where he said to the woman, "I'm not coming back anymore." And he installed that boiler drain that you see here, and he left her with about 4 feet of a hose, like a washing machine hose. And he said, "Listen, whenever you want heat, just put the hose in the bathtub and open this valve and run some water and the radiator will get hot." So the woman said, "Okay, well, I like to take a bath every night. I'm not a shower person. I love laying in the bath. And would it be okay for me to fill the tub up through that same hose?" And the guy said, "Well, I don't see why not. It all comes from the same place." But he's not considering that it's probably not the best idea to fill a bathtub with water from the wrong side of a boiler, not through the tankless coil side, but from the cast iron side. So she did this for a while, and she noticed as time went by that the water was turning color from the corrosion. And she called the guy back and said, the water's got a strange color to it. And he didn't want to go back anymore. So he said to her, "Well, that's minerals. That's good for you. It's good for your skin. People travel from all over to go to places like Saratoga and Hot Springs, Arkansas, and here you got it right in your own house." So she went for that until the boiler failed through oxygen corrosion, and that's where Al got involved. So we learned a few things about these wonderful devices that we call diverter tees. If you don't get any air, it ain't an air problem. Stop bleeding. Diverter tees go back to the 1940s or so, and as we know them today, and the direction of flow is this way. And we used them back then in the 50s on convectors, which were about 3 feet wide. And they always put the piping to and from the convector, the width of the convector, to increase the pressure drop along the run here, so that water would divert through and onward. It's kind of like the OS fitting, the Oliver Schlemmer fitting of the old days. Notice too that we put the diverter tee on the return side, not on the supply side, when we're just using one of them. That's so that it creates kind of a traffic jam up ahead, and the water will go on the service road to the convector and carry on to the next radiator. Bell & Gossett made them, Taco made them. Both of them use these rings to show you which way to put them in. Bell & Gossett painted theirs red. And the goal here was to get the red ring, or the blank ring in the case of Taco, inboard of the pipes that go to your radiator. So if you're using just a return side monoflow tee, that's B&G's trademark, it would be turned this way. So the water coming down looks ahead, and it looks like there's a traffic accident up there. The lanes are closed. So some of the water says, "Well, I'm not going to wait. I'm going to get on the service road and go around." So that's the way it works. If we were feeding up to a second floor like we were on that bathroom, or if we were feeding down into a basement, we'd use 2 of these tees. And in this case, the red rings always have to be inboard. So notice how one tee is facing in that direction, and the other tee is the reverse. It's facing this way. So the goal here is to create a great pressure drop along the run so that more water diverts up the service road through the convector and back into the main stream. So sometimes we need 1 tee, sometimes we need 2. On downfeed, they always use 2. Supposed to use 2. In fact, some of the old-timers would stagger them like that, supply, return, to give us even more pressure drop along the run to drive water down, because the hot water does not want to go down and the cold water does not want to come up. So we got to kind of help it along if we're coming off a basement main that's feeding down to convectors or baseboard that's in the radiator. And by the way, if you're looking at an old-style 1950s convector and you think it looks old, and you're taking it off the main like you see here, and you decide to put in baseboard, you may just remember you may not get any flow through that baseboard, because if you put in 30 feet of baseboard or so, you're adding that much more resistance to flow than you have here. So these are supposed to be spaced the width of the radiator apart, and you got to kind of keep the pressure drop through the radiator to a minimum to induce flow. If it's not heating, chances are there's no flow going to it. It's not air. So let's think about a builder back in those days building those houses in the 1950s. Direction of flow goes that way. You want it to go down to the radiator and come up. And let's say that's a 10,000 BTU radiator or convector. Now, 10,000 BTUs working with a 20-degree temperature drop, well, that's equivalent to 1 gallon per minute. So we want 1 gallon per minute to go down and 1 gallon per minute to come up. Now in the main up here, this is a 3/4 inch main. So the most water you're going to fit through a 3/4 inch main without having a problem is 4 GPM in hydronics. Anything more than that, you're going to get noise. So going back to what Gil Carlson said years ago, whatever goes into a T must come out. If 4 GPM goes in this way and 1 goes down, well then obviously the common piping is carrying 3 GPM because whatever goes in must come out. 3 GPM then joins with the 1 GPM to get us back to 4. Now suppose to make that happen, the manufacturer says you must use 2 of these diverter tees, one pointing one way, the other pointing the other way. But the builder figures he wants to cheat a little bit, so he says, what if I leave out one of these tees? Who's going to notice? All the walls are going to be closed up. So he does that. Now, if he leaves out one of the tees, you're not going to have as much pressure drop along this primary flow. So you're going to get more than 3 GPM here, right? Maybe you get 3.5 GPM. And if you got 3.5 GPM flowing this way, because that T is not there to divert it, then you can't possibly get 1 GPM down here, right? 3.5 plus 1, you got to wind up with 4. So this gets cut in half. So instead of having 1 GPM, you've got a half GPM. Now the big question is that enough to heat the room? The convector is sized for 10,000 BTUs. Can you do that with the half GPM? Well, 10,000 BTUs is the heat that you need on the coldest day of the year. So on a milder day, the half GPM may get the job done. But it's on that cold day that you're going to get called, because that's when this radiator can't seem to heat the room, because it's just putting in maybe 5,000 BTUs instead of the 10,000 BTUs that you need on the design day. But when you go down and you feel that convector, this side's going to feel hot and the other side's going to feel cold, and that's going to look just like an air problem to you, and you're going to be compelled to bleed that radiator. And when you bleed the radiator will get hot eventually, because you'll have changed this flow rate back to 1 GPM by draining the radiator. But keep in mind that you're probably not going to see any air while you're doing this. So, and again, if you don't get any air, it ain't an air problem. So just know that these balance problems look just like air problems, and don't get fooled. This is from Bell & Gossett's design manual from the 1940s. They're showing a 10,000 BTU radiator on the first floor and another one on the second floor. And it's the same radiator, but the difference is on the first floor, it only needs 1 1/2-inch monoflow fitting to work. That would be on the return side. But if we move that radiator up to the second floor, because the run to it is longer and the run back from it is longer, we'd have to increase the pipe size to 3/4 and use 2 3/4-inch monoflow tees down here, even though it's the exact same radiator. So this is the problem that Al and I had in that bathroom that wouldn't heat. They didn't have enough monoflow tees down here to induce the flow up into the radiator. That's what we had to do. Add that second monoflow to make the thing work. So location, location, location. It matters with these one-pipe systems that we call monoflow or Venturi flow. Thermostatic radiator valves seem like a good item to have if you got this type of radiator and you want with the monoflow T and you want to zone it. Now, thermostatic radiator valve is kind of neat because it's not electric. It has this temperature-sensitive head that's filled with a wax or a liquid that's going to sense the air temperature and put pressure on this normally open spring-loaded valve to meter the water that goes through that convector. But what you have to watch out for when you're buying these for monoflow systems or diverter T systems is what's called a CV, because that TRV would go right there. But you got to look at this thing called CV, which is in the catalog, as you see here in the Honeywell catalog. It says CV equals 2.5 for the 1/2-inch valve and 2.7 for the 3/4-inch valve. CV is an engineering term, and CV is always read as a number. And what it is the amount of water in GPM, the flow of water in GPM that causes a 1 pound pressure drop across that valve. So CV you'll see pop up in a lot of things. It's given for packaged equipment, it's given for all kinds of valving. And once we know the pressure drop at 1 PSI, we could figure out the pressure drop at any flow rate or the flow rate at any pressure drop. So if I was selecting for a system with monoflow tees, I would want to have a CV that is very, very high as possible. Meaning that the higher the CV, the lower the pressure drop. Because just by putting the valve in wide open, it's liable to create enough of a pressure drop so that there's no flow at all going through the radiator. So be careful with that. A lot of people put in baseboard and they run it from room to room or from office to office on one long continuous loop. And then you wonder, is it possible to use thermostatic radiator valves on a loop like this? Could I put that in? And your first reaction might be, well, if I put that in, it's going to shut down this room and shut off the flow to every other room. So you might say, well, we can't do that. But one of the things about hydronics is you can pretty much do anything as long as you think it through. And the way to think it through here is if you got baseboard element, you want to use thermostatic radiator valves, just run a smaller bypass. If this is 3/4 inch baseboard, put a 1/2 inch unfinned bypass loop around it. So when the TRV starts to throttle, the excess water, instead of going through the fin tube element, will go around it and on to the next room, and so on and so forth. Nice way to get the job done. So some startup tips before we leave these diverter tees. First of all, if you're doing a boiler and you're changing the boiler, always pump away, because that's going to give you the full discharge pressure of your circulator on the system, and that's going to increase the pressure, which will cause those small bubbles that are up in the system to get smaller. They'll get crushed and they'll be swept back and spit out, so you'll have an easier time. If you pump away from the boiler, you will never again bleed a radiator. Trust me on that. So pump away if you can. If you're working on a job where you're just making some repairs and you drain the system and now you got to get it going again. If it's the flow control valve that has a crank on it where you can lift the weight, by all means lift the weight to take that away from the pressure drop of the system, and that will help you get the thing started up again. See, the problem with the diverter tee system is when you're purging it, you're purging through the main lines. It doesn't necessarily want to purge through the branch lines, especially if they're up on the second floor or down in the basement. So that gives you, once you've drained the system, a difficult time filling it up again. Pitch the main up 1/2 inch and 10 feet so air doesn't get trapped along the way. That's a rule that goes back to the very beginning when these things were first invented. And raise the pressure and lower the temperature at the same time. This was taught to me by an old-time oil heat service manager on Long Island that was working in an area where they had a lot of these systems, and they went into service and they just drained the system and had to get it going again right away. And so they worked with Henry's law that says gases dissolve in liquid in proportion to pressure and temperature. So this fella Howie, who was the service manager, said to me, they'll go in there and lower the temperature, because when water gets cooler, it tends to absorb more air. And then they would raise the pressure almost up to 30 psi, because as you raise the pressure, the water will absorb more air. And by doing that, that's often enough to give them a kickstart to get the thing going. And when all else fails, you could do what another old timer taught me. I wouldn't really take this advice, but I got to share it with you. He said that he never spent no money on any of those expensive tees. He just used standard tees. And I said, well, how did you get the water to flow through the radiator if you're just using standard tees? He says, well, you take the copper tubing between the tees and you squeeze it, crush it with the pliers. I said, how much do you crush it? He says, well, that depends. He says, but you better do it right, kid, because you only get one shot at it. So I wouldn't take his advice, but I share it with you because there's a lot of people out there in this industry who are comical. Now, this is a radiator I looked at in an engineer's office in Germany. And this one caught my attention because in Germany, they use panel radiators. And most of Europe uses radiators like this. They're flat panel radiators. They work on low temperature. They're required by law to have low temperature. I think the hottest water they could send out of a boiler is about 155 degrees. They have a lot more rules over there than we do. And people follow those rules. So I'm in this guy's office with some friends, and we're looking at this radiator. And another thing about the Europeans is most of the jobs that you see run on really small pipe, and the pipe is all within the room. It's all exposed. And when I first saw that in 1990 on my first trip to Europe, I was in Stockholm, Sweden, and I see all this pipe inside the hotel room. I asked an engineer that I was traveling with, why is the pipe inside the room? And he looked at me and he said, so if it breaks, we can fix it. And I said, oh. So he says, where do you put your pipes? I said, we bury them in the wall. We're embarrassed by them. He says, and if it breaks? I said, oh, that's a whole nother industry, reclamation. We just rebuild the whole building. He says, don't those pipes freeze in the wall? I said, yeah, that's another whole industry, thawing out the pipes. So it's a way of producing jobs for Americans. So we laughed. He laughed at me. He says, you people are crazy. Why are the pipes in the walls? So when I got to this place in Germany, I was pretty surprised when I looked down here during the break and I saw this pipe coming out of the wall, and on the return side, it was going back into the wall. So I'm there with my buddies, and we got this German engineer who's lecturing us in German, which we don't speak, but we did have a translator. But he's talking to us about the European approach to hydronic heating, and he's got a flip chart. He's using the universal chalk talk with the flip chart, showing us pump curves and piping designs, and he continuously writes, the symbol for delta and the letter P, and he's pointing at different points in the system, and it dawned on me that this guy and pretty much all of German's engineers in the heating industry are in love with differential pressure. They work with tiny pipes, little flows, and it's a ballet. They get water to flow from this point to that point with very little force. And in America, we have this grand tradition of having basically introduced hot water heating to the world through the form of gravity hot water heating, and we worked with big pipes in those days, which made us use big pumps as we moved into pumps. And we like big pumps, and most contractors really like big pumps. And they'll say, "Oh, the water won't go up there." "Oh, I'll get it up there. Just give me that big pump." And the one I could put a saddle on and ride. So we're going to put that big pump on a cement base, and we're going to have vibration isolation because it's going to vibrate. And then right at its discharge, we're going to put a big valve so we could throttle it down because it's going to be so big, just in case they want to expand on the building 20 years from now. So we're in love with flow and big flow, and they're in love with pressure differential. So I was a little intimidated by this guy because he was so brilliant. I'm just there looking at this stuff. So during a break, I said to my buddy, I wonder why they put the pipes inside the wall, because the walls were made of stone. This is an old building. So he says to me, "Ask him." So through the translator, I asked, the man's name was Mr. Geyer. I said, "Could you please ask Mr. Geyer why the pipes go into the wall?" And Mr. Geyer gets the translation, and he begins to look at me like I'm something to be scraped off a shoe. And he says, through the translator, tell the gentleman the pipe does not go into the wall. This is the pipe. So I said, "Wait a minute, this is the pipe?" "Yeah, this is the pipe." So I said, the pipe is square?" So he says, "Yeah, the pipe is square. The pipe is square." So I said, "Why is the pipe square?" Now, have you ever asked a question that's so monumentally stupid that you're trying to stuff the words back into your mouth even as they're coming out? Why is the pipe square? So this has to go back and forth through the translator, but it comes back. Are you ready? Mr. Geyer says, "The pipe is square because the corner is square. Square pipe, square corner fits. Round pipe, square corner, not so good." So I said, "Oh." So my buddy says to me, "Well, that was a stupid question." So I said, "Yeah, well, you should have asked it." So we're looking at this thing, and I'm just marveling at the wonder of it all. And my friend says to me, ask him, how does he get the water to flow through the radiator and not through the square pipe? There must be some kind of a diverter tee in there, or something. There's no monoflow tee or anything in the square pipe. But what makes the water flow through? So I asked the translator, and Mr. Geyer writes on the flip chart, delta P, meaning that the difference in pressure between this point and this point is greater through the square pipe than it is through the radiator, because the pressure drop through panel radiators is almost non-existent. So my friend says to me, "Tell him that can't work." So I said, "But we're looking at it, it's working." He says, "No, tell him it can't work." So I said to Mr. Geyer, I don't see how this can work. You should know about these things called diverter tees. So I take out a pen and a paper, and I draw for him what I thought was a really nice cutaway of the drawings I was showing you earlier of these Bell and Gossett diverter tees. Well, Mr. Geyer sees this, and he recognizes this for what it is, which is a cumulative pressure drop. The more of them you have, the worse it gets, and the bigger your pump has to be. So he looks at this. The guy's got a PhD in engineering, right? So I have a bachelor's degree in sociology. So he takes the paper, he balls it up, and he throws it at me and calls me a dirty name in German. So my friend says to me, "Good question." So I said, "You should have asked it." So he says, "You know what? Tell him this can't work because every time the water goes through here and comes out the other side, it's going to be cooler, and it's going to cool the water that goes to the next radiator. And by the time they get around to the end of this run in this big office building, the radiator is going to be too cool. The water is going to be too cool to heat those last offices. Tell him it won't work." I said, "You tell him it won't work." He says, "No, why should I get involved in this? The guy already knows you're an idiot. Don't get me involved." So I said, "Okay, what about delta T, difference in temperature? How are you going to make that work?" So Mr. Geyer then takes us down the basement. He was very proud at this point. He takes us down the basement and shows us this piping arrangement that I had never in my life seen. This guy had a circulator, and then he had a four-way valve. which can make the water go in different directions. And then he had a timer. So for every half an hour, he's got the water going clockwise around this big loop. And then the circulator shuts off, it switches the four-way valve, and the water now goes the opposite direction for half an hour. So every half hour, he's reversing the flow through the entire system. This guy gets the hot water first. This time, half an hour later, the other guy gets the hot water first. And that works. So it's very hard to argue with success, and that's what they were doing in this building. And since then, at heatinghelp.com, over the years, on the wall, we occasionally get a guy that'll come on and say, listen, I just did my first radiant job. I installed 1,000 feet of 3/8 inch PEX tubing in the concrete, and now I need to know what size circulator. So somebody will say, well, how many zones is that? How many circuits is that with 1,000 feet? And the guy will say, what's a circuit? So then we'll realize he installed 1,000 linear feet in one continuous circuit of 3/8 inch PEX tubing, and now he wants to pump through it. So, we might suggest you go to the fire department, get one of those big trucks. They've got pumps that could do that. Or better yet, we tell them about the trick with the four-way valve and the timer and reversing the flow, and often that will get the guy off the hook, because if the radiant is in a slab and you can get it hot, you pretty much get it to work. So there you go, lessons learned from traveling overseas. Now, a one-boiler system, using this concept of pumping away. This is kind of neat because we're going to put everything on the supply side, and there's nothing that I've invented here. This is all just classic piping that's done on the big, the big stuff, the engineering stuff. We're just going to make it work on a smaller job too. First of all, we're going to have one drain valve that's going to be the purge valve for the whole system. No matter how many circuits you've got, that's going to be the purge valve for the whole thing. And there we got a service valve that we're going to use with the purge valve. We're going to purge to the top of the boiler, not through the bottom. Over here, we got the air separator and the air vent, and there's our compression tank, and we're going to bring in the fill valve at the point of no pressure change. So that will never be affected by the circulator. It will never be able to feed once when the circulator comes on, giving us an undersized compression tank. Out of here, in this case, we're using two circulators. We've got two flow control valves, which stop gravity circulation on the circulator that's off, and two more service valves. So by closing these three valves, I'm able to get at anything that's in between without having to drain the system, without having to go upstairs. That's nice. When I first start up, I shut these two valves over here. I shut this valve over here. I open the fill valve. Now the water goes this way, so I open one of these valves. It fills the system. The water comes back. It fills the boiler, and it comes out of the drain. And then I close this valve, and I open the second zone, and the water then shifts to this way, fills up here, comes through the already filled boiler, and when it's running air-free, I shut off the fill valve, I open all the valves, I start it up, and now that I'm pumping away, these circulators are going to send their full discharge pressure, their full differential pressure out toward the system, which is going to take these little bubbles that are trapped out there. It's going to crush them and sweep them back. They're too small to get stuck, and they're going to come right out and get spit out of the air separator. If you pump away like this, I guarantee you will never again bleed a radiator. You won't have to go upstairs. And that's kind of nice because, if you're an installer, the last thing you're doing is up there trying to move furniture or move fish tanks or brake fronts to get at a radiator. This is the time when you're touching white rugs and white walls, and the people have the final payment. They don't want to pay you because you just messed up their house. So isn't it nice if you could do all that from the basement? Here's the same idea using zone valves instead of multiple circulators. So we got one circulator and zone valves, but again, everything is positioned between these valves for service down the basement. Standing up, pumping away is pumping away from the compression tank, not from the boiler. So it's kind of nice. You're using less equipment here. You're getting much quieter systems that don't air bind, that are easily serviced. Very, very nice way to go. Now, suppose I do want to use more than one boiler. This is what I did in that house in Upper Montclair, New Jersey. So when you're doing primary, secondary, which is what we have here, the primary circulator in the main line always gets the compression tank, the real compression tank. The secondary circulators here see this common piping, this T, as their compression tank. So we always want to pump down, in this case, into the boiler and away from that common piping point, which is the secondary pump's compression, point of no pressure change. It's compression tank. So there again, if I have non-condensing boilers, I want to blend some of the hot boiler water over here to bring the temperature in the return above 140 degrees to prevent condensation inside of a boiler that's not a condensing boiler. So this is a good way to go, because here I'm taking the same supply temperature into both boilers off of my primary. So if this were coming in at, say, 150 or 160 degrees, no matter which boiler was operating, we'd be dealing with 160 degrees going into that boiler. Another way that it's done is like this, where we're hanging the boilers like curtains on a rod. This isn't as good, because let's say this is looking for 180 degree water, and this first boiler comes on, and it brings the water from, say, 160 up to 175. So now the water in this pipe is 175 degrees. This guy over here brings the 175 down and brings it up to 180. So this one's going to be running nicely. This one's going to be short cycling like crazy. So if I do it the other way, where I'm using manifolds to keep the temperature going to both boilers the same, I avoid this challenge that you run into when you hang the boilers like curtains on a rod. Now, another type of one-pipe system is the loop system. And the loop system comes about with the invention of baseboard, which is pretty much attributed to Mel Dubin, who founded the Slanfin Company when he came back from World War II. And that was on Long Island, not far from where I live. And Mel told me once that he decided to position his company right there because he wanted to be as close to Levittown as he could possibly get. And I'll tell you about Levittown later, but that's where they did 17,000 radiantly heated houses, tubing going into the slab, and Mel had a feeling that that stuff was going to fail over time, and it did, and Mel wanted to be real close there with his baseboard, so he did okay, and he was a great guy and a good friend, and I miss him very much. Passed away recently. So with the loop system, we're taking this pumping away idea, and we're going through a continuous loop of baseboard back down. So it takes a lot of the thinking out of it, but what you have to be careful about is there are limits to how far you can go on baseboard loops before you run out of heat. So the rule of thumb for this, based on the manufacturer, is never go beyond 25 feet for half-inch baseboard and never go past 70 feet for three-quarter-inch baseboard. Otherwise, you're going to have a problem. So one time I was doing a seminar, and a guy comes up to me during the break, and he says to me, Dan, he says, I put this baseboard loop into this big VFW hall where they got this big area that they rent out for parties, and then it goes to offices. And I got this one big loop, and I can't seem to get the end hot where it goes to the offices. I said, well, what have you been doing? He says, well, I've been bleeding it. I said, of course you have. And I said, when you bleed, do you get any air? He says, no, that's the damnedest thing. I don't get any air, but I keep bleeding it. I said, well, if you don't get any air, it ain't an air problem. Why are you bleeding it? He says, well, what else am I supposed to do? I said, well, how many feet of baseboard element do you have on that one circuit? He says, well, all in all, it's about 375 feet. I said, you got 375 feet of three-quarter-inch fin tube on one circuit, you want to know why the end is cold? He says, yeah. I said, the end is cold because you ran out of heat. You can probably chill meat with what's coming through that radiator at that point. You ran out of heat. He says, how could I run out of heat? Everything's connected. The circulator's running. How could I run out of heat? So I said to him, let me see if I can make this visual for you. And let me see if I can make this visual for you. I said, imagine a British thermal unit as a little man who lives in the boiler and works in the radiator. And he's a little British thermal unit. So he's wearing a raincoat and a bowler hat, and he's carrying an umbrella, and he's got a briefcase, and he's the heat. And he lives inside the boiler, and he goes to work in the radiator, and he travels to work on this thing we call the flow rate. That's the water flowing through the pipe. Guy says, I like this. I could see this in my mind's eye. So I said, okay, now since it's a three-quarter-inch pipe, we don't want to move more than 4 gallons per minute through that, because otherwise you're going to get a lot of noise. And the baseboard people tell you no more than 4 GPM. That's it. So now if it's 4 gallons per minute, if we're working with a 20-degree temperature drop, the water goes out at 180, comes back at 160, giving us an average water temperature of 170. That means that each GPM is 10,000 BTUs. That's what it can carry. So since we got 4 GPM, that means that we got 40,000 guys that are going to go to work. He says, I like this. I could see this. I said, great. Work with me here. So the train starts up, and the 40,000 guys, they get on the train, and they head out into the baseboard. Now they're moving into baseboard element that has air moving across it. So that's like getting off the train. So every linear foot that they travel, about 600 of these guys hop off the train. That's where they work. They're going up to their office. So every 600 BTUs come off every foot. So by the time you get past 70 feet, you're basically out of guys. You don't have any more guys. The train's going, but there's nobody on it. That's why you don't have any heat. The guy says, wow, I like that. I can really see that in my mind's eye. I said, okay, so now you know what you got to do, right? He says, yeah, I got to get a bigger circulator. So I said, there's nobody on the train and you're looking for a bigger locomotive. You want to bring nobody there faster. So, no, that wasn't the answer, bigger circulator. But the answer was, of course, to split the zone up into zones that are no longer than 70 feet, which is what he had to do. And again, he says to me, well, who's supposed to pay for that? And I said, well, you are. He says, why should I pay for it? I didn't know. I said, because it's tuition. Now you know. This is the price of learning about this stuff. So, primary, secondary, one pipe, primary, secondary. By the way, that fellow Gil Carlson, who was my teacher, he invented primary, secondary in 1954 on a problem job in New York City, and it went on to become an industry standard. So he was a guy that did a lot of stuff. But the primary, secondary works like this. So we got the primary circuit here, and we got the compression tank in the primary circuit, and then we got the secondary circuit over here. And we keep these tees very close together. We want to keep them so close together that there's very limited pressure drop in the common piping. So this is the common piping right here. And imagine if this secondary circulator was off and the primary is on. Well, as it enters the tee, whatever goes into a tee must come out. But if it can go 6 inches, these are not diverter tees here. This is just wide open pipe. Can you see how it'll go straight through without any flow at all going here? So if I keep the common piping pressure drop to a minimum, these two circuits can be hydraulically disconnected, meaning that one circulator is not going to affect the flow in the other circuit. So you could have a big circulator and a small circulator operating side by side, and one's not going to pick on the other. But if I start to move this piping further apart, like if I moved it out to here, can you see how the pressure drop along this run is now getting longer, and water may begin to look at this as an alternative to going straight? Can you see that? Yeah. And suppose I take this pipe and hook it in down here like this. Wow. Now if the primary is on and the secondary is off, can you see how the water might go through here and just flow backwards to that circulator, which is off? That's possible. So we don't want that to happen. So in primary, secondary, we always keep the tees as close as we can get them, ideally no further than 6 inches apart. That's why you'll see this always like this. And there are companies that make specialized fittings, like Taco has these fittings that are primary, secondary. There's your secondary connections. There's your primary. Webstone, which was just recently purchased by NIPCO, has a delightful valve that's used specifically for primary, secondary. And what I like about this valve is there's your primary flow, and these are your secondary connections. And when I'm first filling the system and I want to purge everything, I want water to flow through that secondary circuit. So all I have to do is move this ball valve this way. It's going to drive the water through the secondary circuit, and then I open the ball valve open the ball valve again, and just leave it wide open. So that's a great product right there. So when we're doing primary, secondary, each circulator becomes responsible for only the circuit that it's in. So this guy has got to deal with the flow rate and the pressure drop of only that red loop. And the secondary circulator deals only with this yellow loop. So flow rate and pressure drop here. So they're hydraulically disconnected, and they're sharing this one little bit of pipe here. So knowing that, let's look at some numbers. Suppose, for instance, we had a primary circulator that could move 20 gallons per minute. Well, if the secondary is off, 20 gallons per minute is going to sail right across the common piping and go that way, and you'll have flow in here and no flow at all up here. And then if the secondary circulator comes on, let's say that's 10 GPM, well, whatever goes into a T must come out. So if 20 goes in courtesy of the primary, and 10 gets pulled out courtesy of the secondary at the same instant that 10 gets shoved in this side, well, then what has to be going on in the common piping, of course, is that 10 GPM is flowing that way, and everything works. Now let's make it more interesting by saying the primary is 20 GPM and the secondary is 20 GPM. Well, we could do that too, because when the secondary comes on, this common piping is going to see absolutely no flow at all. There'll be still water right in this piping because the 20 just goes this way, comes down. Whatever goes into a T must come out. And to make it even more fascinating, let's do this. Let's make the primary circulator 10 GPM and the secondary circulator 20 GPM. Now watch this. 10 GPM flows into this port of the T. 20 GPM gets pulled out of this port of the T. Now, how's that possible? Well, it's 20 GPM, 20 GPM, 20 GPM, 20 GPM going in here. And when it goes in there, the extra 10 goes backwards. So you got 10 going this way, 10 going backwards, giving you 20. It's coming around here, and 10 goes that way, being pulled back by this circulator. So that's how we pull the rabbit out of the hat. And what makes this even more fascinating is this water here has been through radiation already, so it's coming back cooler than the water that went out. So we got 10 GPM of relatively cool water that's mixing with 10 GPM of hot boiler water, and that's giving us a mixing point here that's being done. We have a 2-temperature system that's being done without benefit of any kind of valving, no kind of tempering valve. And to figure out how that happens, we use this formula called the blending temperature formula, which works like this. We take the hot flow rate times the hot temperature, and to this we add the cold flow rate times the cold temperature, and that's going to give us the mixed flow rate times the mixed temperature. So a little math here. If this is 10 GPM coming out of the boiler at 180 degrees, and this is 10 GPM coming back from that secondary circuit across the common piping at 160, it's going to join together at 20 GPM at some temperature. Well, the way to know it, you got to do a little algebra here. So 10 times 180 plus 10 times 160 equals 20x. So you do the stuff on the inside of the parentheses first, and that's going to give you the 170 degrees. Easy? So let's look at this done in a way where we're hanging stuff like curtains on a rod. This is a big job. It's a 250,000 BTU boiler, and we're working with different zones. These are high temperature zones. This is baseboard, which is 40,000 BTUs. This is an indirect domestic water heater, which is 125,000 BTUs. And these are 2 radiant zones, each 40,000 BTUs. And we're making the radiant temperature by using 3-way valves. So we're blending return water into supply water to give us the lower temperature right there. So some of the rules that you follow with this, and by the way, these valves here, those are those Webstone valves that help us with the purging. That's all. That's just for startup. So the compression tank is going to go on the boiler, and we're going to pump away from the compression tank, and this is our primary loop. Everything else is a secondary loop. Now, the rule with this is we always take the hot stuff first. So the baseboard manufacturer says, I want 180 degree water. The indirect manufacturer says, I want 180 degree water. So we take the hot stuff first and the cooler stuff, the radiant, last. Common sense, right? The hottest water out of the boiler should go to the hottest need over here. And we always start with the lower load before we take on the bigger load. So hottest first, going from lower load to hotter load. Now the problem with piping this way without using those manifolds is that the baseboard guy wants 180 degrees and so does the indirect guy. But that can't be, because I'm coming out of the baseboard at 160, which is going to lower the temperature to probably 170. So this guy's going to get 170 instead of 180. And I ran these numbers and found out that to make that work, pipe this way, I would have to run my boiler up to 190 degrees to make this system work. So to save fuel, let's pipe it in a different way. Let's just use these manifolds. So rather than pipe these individually, separately, we're going to come off with a hot manifold so that both the baseboard and the indirect see 180 degrees on the supply. And when it comes back into a return manifold that's going to blend these 2 temperatures before it sends it on to the radiant. And I'm going to do the same thing with the radiant, where both radiant circuits are getting the same temperature water. And this works out much better. And when I run the numbers, now I could save 10 degrees constantly on my boiler. So I'm running up to 180 maximum rather than 190. So these manifolds do save fuel. So that brings us to 2-pipe systems. And there's a big advantage to 2-pipe systems because the water to every radiator is going to be the same temperature. Look at this direct return system. The water comes out of the boiler and it goes up. And if it's 180 degree water traveling through an insulated pipe, the radiator on the first floor gets 180 and so does everybody else. So that's a big advantage in a large building over, say, running baseboard if you can't go over 70 feet, or running diverter tees where the water keeps getting cooler and cooler, lowering the supply temperature to the subsequent radiator. So we call this direct return because it's like a ladder, and the first rung on the ladder gets the flow first. So it's the first to supply, the first to return. And the top rung of the ladder is the last to supply and the last to return. So in a system like this, we definitely need to have balancing valves on every circuit. Otherwise, the water is just going to go through the first floor, the path of least resistance, back to the circulator suction side. So that's direct return. Now look over here. You see the one return pipe. We're going to move over to reverse return, and we're going to add a pipe. So the advantage of reverse return is we don't have to balance this as long as all the radiation is the same, because the path to and through everything is the same distance. So the first one supplied is the last one returned. That's why it's called reverse return. The last one supplied is the first one returned. So the path to and through and back from every radiator is the same distance. So if you're working on a design and the main pipe is no bigger than 2 inch, it usually pays to use reverse return. And if your main line is bigger than 2 inch, it pays to use direct return with the balancing valves. Classic 2-pipe stuff. Now, direct return with thermostatic radiator valves. These would go here. And each one of those is going to sense the room temperature, the room air temperature, and it's going to throttle. But the challenge with this is it has no way to talk to the circulator. So I don't want these things closing and create a situation where I'm deadheading the pump and I'm liable to blow it up like I did on that one job on Long Island. So what we use here, or what we've traditionally used here, is a bypass line. And in the bypass line, we're going to have a differential pressure regulator, which is aptly named because it regulates differential pressure. So we set this up in the beginning so that as these thermostatic radiator valves, which are non-electric, begin to close, whatever is not flowing through that particular circuit will flow through here. So these effectively nail the circulator on a point of its performance curve, and it never moves off that point. And they're pretty simple to use. Here's one in real life. It's sort of a relief valve that doesn't pop open. It meters itself open, and it's got a knob on the top. So the way you would set this up is you would start out when the job was new with all the control heads removed from your thermostatic radiator valves throughout the whole building. You then set your circulator, and this thing would be in the boiler room from the pump's discharge back to its suction side, and you would turn this knob on the top while feeling this pipe. And as soon as you felt hot water creeping through here, you would turn the knob back and leave it like on a hair trigger. At that point, it's all set. You can put your thermostatic radiator heads on, and when any one of them shuts down, the flow that's not going through that radiator will flow across here. We don't see as many of these around anymore as we used to 10 years ago, because nowadays we've got these smart pumps that operate on ECM motors, and they know when the flow rate is not right, and they know when the pressure's building, and they just automatically sense that and slow down the flow and slow down the speed that they're running at. So they do all that automatically. But if you don't want to go for the expense of the smart pumps, you can use a differential pressure regulator. It does use more electricity on the pump side, but that's a trade-off. Okay, so flow rates. These are the normally accepted maximum flow rates for hydronic heating systems. And you can see this in the boiler manufacturer's equipment in the holes that they select. For instance, we looked at baseboard before, and 4 GPM would be the maximum flow that you could put through baseboard. So they list that in the catalog. They say 40,000 BTUs, that's it. If you were to look at a boiler manufacturer's catalog and saw a boiler that was rated at, say, 450,000 BTUs, which working with the 20-degree temperature drop would be 45 gallons per minute, that boiler is going to have a 2-inch hole in it. So by knowing the flow rate and the hole size, you can understand the thinking here that it's all designed to work with this traditional 20-degree temperature drop, with the great exception of the modulating condensing boilers, which have smaller holes in them. Now they do that on the manufacturing level to force you into using greater temperature drops across the system, because when you're working with mod-cons, or modulating condensing boilers, the cooler the return water is, the more condensation you're going to get out of the flue gases, and the more efficient the boiler will be. But I used this trick for years when I worked in the field, because if a circulator doesn't have the labels on it, like you go on a job, there's no label on the circulator to tell you what it is, I would look at the flow rate based on the pipe size that was coming out of the boiler. So if a boiler had no label on it, I'd look at, if I see a 2-inch pipe, I know that that's probably going to be 45 gallons per minute, and it's going to be 450,000 BTUs, and whatever information you have to work with, you can confirm that. But if somebody called me when I worked for the pump manufacturer and said, I need a pump, I don't know what size I need, I'd say to him, well, what size pipe is there? And if he says a 2.5-inch size, I would size him a pump for 85 gallons per minute, which is the maximum flow you can flow. And I'm figuring whoever designed this job in the beginning, if they could have got by with a smaller size, they would have used it. So if I see 2.5, I'm going to size for 85 gallons per minute. And but you also have to know the total dynamic head. So that's based on the longest run in the system. And if the guy doesn't know what that is, I will have him measure the building itself. So go outside the building and stand on the corner, measure from here to the end of the building, up to the top, over to the opposite corner, assuming this is a big cube, say, down, across, and back. That's the longest piece of pipe you could put in that building. And if the guy tells me that's 300 feet, I'm going to figure 6 feet of pump head for every 100 feet of pipe. That's based on the resistance to flow that you would see at a flow rate that is the maximum that would fit through the pipe. So I would size for 85 gallons per minute at an 18-foot head. If there's 300 feet of pipe, I'm figuring 6 feet per 100 feet. And the years I worked, the 19 years I worked for the pump rep, I did that probably thousands of times and never got a pump back. And if I was looking at a pump curve and I came up with, like, there's one that's bigger and one that's smaller, not the exact one I want, I would consistently pick the smaller of the two. And again, it worked every time. So there's a quick and dirty way of sizing circulators for existing jobs when you don't have all the information on what's going on. You don't have the original building plans. Now, speaking of the power of the pump and measuring the longest run, which you see here, that's that high point, I want you to think in terms of the power of the pump and why water flows the way it does. So when we leave a circulator like this and we get to that T, we're entering a T. Whatever goes into a T must come out. So here we have an acronym that stands for very, 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 very strong. That's what that is. The pump power right there. Now we go a little further and we lose some energy. So now we're very, very, very strong. And here we're very, very strong. Here, go with me now. Very strong and just strong. You see how the energy dissipates by friction? And then we go all the way across the top. And over here we're less strong. And then even less strong. And then much less strong. And then I'm getting tired, and finally IDMA, which stands for I'm dragging my ass. Now, if you were the water and you had a choice of going between these 2 points, very, 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 very strong and very, very, very strong, or going from very, 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 very strong to I'm dragging my ass, what would you do? Yeah, I would too. I'd go this way because that's where the greatest differential pressure is. It's like putting 30 pounds of air in your tire with a compressor that's set at 100 pounds. It's going to go ka-chunk, 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 right? But if you put 30 pounds of air in your tire with a compressor set at 31 pounds, it's going to go ka-chunk, ka-chunk. It doesn't want to go that way. It wants to go where the greatest pressure differential is, and that's between these 2 points. Now, I want you to notice this as you move further away from that circulator and get up here. Notice how these 2 points of differential pressure begin to approach each other. This is why we put balancing valves in, because as these begin to approach each other, and it's all about the delta P, the flow rate slows. Ka-chunk, ka-chunk. You see it? It's at the top floor. The water's moving very slowly because we're not balancing properly. And low flow means no heat, and you're going to go up there to that top floor with a key and a rag and a can, and you're going to bleed radiators that don't have any air in them. And when you bleed, you won't get any air. And when you don't get any air, you got to know that ain't an air problem. So stop bleeding. All right, 2-pipe system on primary, secondary. Here's one way to do it. Now again, the big advantage of primary, secondary is everybody's going to get the same temperature water. So as we leave at 180 degrees, on this, what we call a crossover bridge, going into the return, is 180 degree water, as it is here, and here, and here. And this is the same job we looked at earlier. We've got 245,000 BTUs, 125,000 BTU on the indirect, 40,000 on the baseboard, and the 2 radiants. So since we're working it this way, we're going to take the hottest stuff first and the coolest stuff afterwards. And it really doesn't matter which way. I mean, I've reversed it because everybody's getting 180 degree water, so I reversed it. It still worked out the same way. Works like a dream, but it does cost more to do. Now, when we figure out the size of the main, the way it's done on the engineering end is we look at the blending of these temperatures coming back. And when we come back, we get a temperature over here and a temperature over there. And that tells us the temperature that we need and the pipe size that we need. I can tell you one thing about primary, secondary, though. If you're working with a 20 degree temperature drop on systems that have both high temperature stuff and radiant stuff, you're leaving money behind on the job because you're working with temperature drops that are too close together at 20 degrees and you're using pipes and valves and fittings and pumps that are too big. So if you want to get a better handle on this, go to heatinghelp.com and get a book that I wrote called Primary Secondary Pumping Made Easy, and it takes you through all the math on how to figure out the pipe sizes to save the maximum amount of money on every job you'll ever do that involves primary, secondary, with any kind of radiant mixed in. Air. What would we do without it? This is William Henry. I mentioned him earlier. He's the guy that came up with Henry's Law that said gases dissolve in liquid in proportion to pressure and temperature, and Henry's Law is a big part of our life. If you want to see it every day, just go out and get yourself some Canada Dry club soda or anybody's club soda or anything that's got carbonation in it. Shake it up, open the cap, and you will experience Henry's Law. The gases stay dissolved in the liquid as long as the pressure is in there, and the pressure is in there because you're trapping that gas under the cap. But as soon as you release the pressure drops and those bubbles get blasted out of the bottle, and that is Henry's Law. So we use it all the time in heating. This is a compression tank, not with a diaphragm. It's the old school compression tank. We fill it 2/3 with water, 1/3 with air. Always put the air on the top. Too difficult to try to get it on the bottom. Ha. So now what happens here is if this is attached to a hot pipe in the system, the heated water in the system is going to rise up by gravity and bring the cooler water down. Now Henry's Law says since you're not pumping water through here with the circulator, and we can't do that, remember, the circulator cannot add or remove water to the compression tank. Since we're not pumping through it, the water in the tank is going to be cooler than the water in the system. So when you get this kind of a gravity circulation naturally happening here, the air that's in the cushion gets absorbed into the tank water because of Henry's Law. And that cooler water, which has air dissolved in it, is going to come down into the system, and it's going to join the flow of the hot water going out, and it's going to wind up coming out of solution and be in a radiator somewhere. So every time the system cycles, we lose some air out of a radiator through an air vent, and that gets replaced by fresh feed water, which is cold, which contains air, and the level in the tank goes a little bit higher on each cycle as we lose the air until finally the tank is waterlogged, and somebody's got to go out there and blow the water out of it and replenish the air. So if we could prevent this gravity circulation, we can prevent the loss of that air cushion. And the way that's done is to use this device that B&G came up with before I was born. It's called an air troll tank fitting. And it works by having this little cuff that you see over here and this tube that sticks up above the water level in the tank like a periscope. So on the job, it looks like this. So we separate air down below with an air separator, rises up by buoyancy, and it goes up into the tank, and the hot water that's rising up with it can't go any higher than this because it's the top of the tube. Right? That's higher than the water level. And the hot water coming up can't get under this cuff because hot water won't sink, it'll only go up. So by setting it up this way, you effectively stop the gravity circulation between the tank and the system, and you won't lose the air that's in the tank. So there's still plenty of those compression tanks out there, and if you're dealing with one that's waterlogged, that's the solution. Also, if there's a gauge glass on the tank, be careful about that upper valve over here, because the gauge glasses are supposed to be kept closed all the time, because that upper valve on the gauge glass set is not wet. It's in the air, and that will leak air. And as soon as the water rises up and wets it, the gauge glass valve will never leak. But that's a good source of losing the air. So if you got a gauge glass on a big commercial tank, keep the valves closed all the time. Diaphragm tanks were pioneered by Amtrol out of Rhode Island, and they were the first to do this. They came up with the idea of rather than collecting the air in a tank, they're going to expel it from the system, and they're going to work with this diaphragm that has water on one side and system pressure on the other that we charge up with a valve. And this is the prototype of their first tank. They gave me this. They made this out of 2 street lamp blanks, and they put a rubber diaphragm in between, and they hung them from a basement ceiling. Here you see it's upside down, but that proved the concept that you could trap air on one side and water on the other. And as they began to make these tanks in the early days, they didn't have a Schrader valve on there, but they used a chunk of dry ice. They put the dry ice on the air charge side, and it would of course evaporate and put carbon dioxide in there, and they knew how much dry ice to use to create a 12-pound pressure inside the tank. The problem was, as time went by, is they found out that the rubber diaphragm that they use is a semi-permeable membrane, like a balloon, and a balloon will lose the air right through it. It's by osmosis, so there's more pressure on one side than there is on the other, so the air just moves right through the balloon. And it was doing the same thing in these tanks, and Amtrol expects tanks to lose pressure at a rate at least 1 pound of pressure per year. And that's why they now give you the Schrader valve, which you could use to pump the tank back up again. But you really can't pump it back up if it has water pressure inside of it. So you got to disconnect it from the system. But before you throw those tanks away, check the pressure, because it could just be that the air moved through the diaphragm and got released through an air vent out in the system. Air scoops, also widely used by Amtrol and other manufacturers, scoop air, and they work by having the air bubbles at the top here. So we're looking for what engineers call laminar flow, which means that it's not turbulent. Laminar is the opposite of turbulent. If you've ever flown in an airplane, you know what turbulence is. So they'll tell you that they want this thing installed in a straight run pipe, at least 18 inches long, and with nothing in that pipe. It's got to be full size, horizontal, straight run. What you'll often find on job is this thing is screwed right into a street elbow. So you've got very turbulent water, and the air can't get scooped off. But the air's got to be at the top of the pipe to get pushed off on this kind of a plow into this lagoon and spit out of the system. So if it's not installed properly, it's not going to work. If it's not installed properly, it's not going to work. This guy put his air separator on the coal feed line going into the system. Now the air comes out of the system when the water gets hot, so you need a boiler to do that. So putting an air scoop on a cold water feed line isn't really the way to go. But this is the stuff that we see on heatinghelp.com all the time. Come and visit. Spirovent is a company out of the Netherlands that was founded by a family called the Raffelsons, and I've visited with them over there in the Netherlands. Lovely people. And they came up with something that was very different from an air scoop, and looks like this internally. They have what is a piece of an element from a convector that they also made, and they worked with a principle of adhesion and collision, or collision and adhesion. So they could take these tiny little bubbles that are called micro bubbles, and you've seen micro bubbles if you've ever poured tap water into a glass and it looks milky. That is not milk. That is microbubbles. And if you let the water sit for a while, it just goes clear again. So those are the bubbles that the Spirovent type of an air separator will collect. And it does it by having those microbubbles just go through this nest of tight wire, and it just clings to the surface and then floats up into this lagoon and gets spit out of the Spirovent. And what was nice about this is it can be installed in either direction, and it doesn't need any kind of special approach piping. And they put themselves on the map in the early 90s by coming to America and having these displays that you've probably seen at trade shows, where they pipe a Spirovent, which is clear, see-through plastic, into a plastic rig, and they've got a circulator in there, and they give you a bicycle pump, and you can plunge a big slug of air in there, and you watch it goes through the pump and it spits it through the Spirovent. The Spirovent just laughs at those bubbles and just spits them right out. So it was a pricey item compared to an air scoop, but it became very popular because it did work, and it did get rid of the air. But any air separator will get rid of the air eventually if it's installed properly in a closed hydronic system. Honeywell bought from a company called Sparco this air separator, and they renamed it the PowerVent, and it's similar to the Spirovent. Came out shortly thereafter, but they couldn't use, of course, that proprietary element that was inside, so they decided to use a fitting brush. And I love this when I first saw it, because if you can make an air separator out of a fitting brush, which to me said, if you can't make money in America, you're just not paying attention. So there you go. Bell & Gossett came out with their wonderfully named enhanced air separator, which also has a fitting brush inside of it, so there, and also works pretty well. And Taco, no fitting brush, but it works with a vortex, and it's called a vortex, but it takes the water in and spins it in a circle, causing the air to go to the middle, the heavy water to go to the outside, and it spits it out that way. Watts has a similar thing, and theirs is called a coalescing media and the dual flow assembly, and I love the names that they use for these, and it's well done marketing, coalescing media. So you say coalescing media, I say fitting brush, so it all gets rid of the air. Taco's got a big air separator that uses these Paul rings, which are very tiny, and this probably holds thousands of them. And again, the air separator is nothing more than a wide space in the road. When the water gets in there, it has to slow down, and the air bubbles will collide with and cling to all these little surfaces that you see in here. So this whole air separator is just loaded with these things right up to the top. And then the air gets into this quiet lagoon away from the flow and just comes right out of a high capacity air separator, and it's gone from the system for good. Bell & Gossett years ago came up with what they call the roll air troll, which has an opening on a tangential opening. So it's on the side of the device, in and out, and when the water comes in, it's going to spin in a whirlpool like that. And they have this baffle in the center. So the water has to squeak by the edge of the baffle to go through the strainer and get out. And in doing so, it has the least amount of air in it, because it's going to spin like a vortex, making the air, which is lighter, go to the middle, and the heavier water that has less air in it is going to go to the outside, and that's the way they make that work. So these are all common air separators that you'll see out in the field. Now, a little bit about mixing low temp and high temp, which we talked about earlier. If we're going to mix radiant heat in here, let's see how we could do that several ways. Or actually, one way that's used very commonly. This is done with a three-way mixing valve. You see these all the time. This is the primary load over here. It's got the compression tank here. The secondary circulator is using this connection and the common piping as its compression tank. So we're pumping away from that. So the radiant load is going around here. It's continuous circulation, moving around and around and around. And we're going to vary the temperature with this mixing valve. There's the primary load. So this is 108 degree boiler water going around here. Now we've got a three-way mixing valve. This is the hot port, the relatively cold port, and the mixed port over here. And then we've got a flow control valve to stop migrating hot water from entering this flow. So now this is the challenge with this using a mixing valve. The flow is going this way, the hot water comes up, the cold water comes down. The return water has a choice of either going back to the radiant, mixing with hot water to keep the temperature up, or going completely back into the primary flow if the radiant load is satisfied on temperature. So it's continuous circulation, and we're varying the temperature. The problem, though, is the compression tank is located on the primary circuit. And when this mixing valve is satisfied and goes to full bypass, this port, the hot port, is going to close. And all flow to it is going to stop. At this point, this circulator is isolated from the compression tank. It can't get at this T that it uses as its compression tank. So the pressure will drop off the suction side of the circulator, and it will begin to cavitate. So you can wreck the circulator on your radiant load by using a three-way mixing valve, as you see it piped here. So the way we get around that is, rather than use a three-way mixing valve, we're going to use a diverter valve. So this is a three-way mixing valve. It has two ways in, hot, hot, cold, mixed, and one way out. Two ways in, one way out. This is a diverter valve, which has one way in and two ways out. And by using this, which looks the same on the outside but works a little different internally, we're able to move the diverter valve over here. So your continuous radiant circuit is going around that way, your primary is going around that way, but now look, this is the flow. I've reversed this check valve. So now when the diverter valve moves its position, the hot water will come here. And by doing this, when this port closes, I still have access, pressure-wise, to the compression tank. So this will not cavitate. It would cavitate with a three-way mixing valve, but it will not cavitate with a three-way diverter valve. So these are a pretty good way to do radiant heat. For the fun historical part of the talk, classic radiant, all about places where I grew up. I think you're going to like this. It's a good story. And it's an old story. It begins back a long, long time ago. You think radiant is relatively new, but it's not. You think it started, after World War II, but it started way before that. It started in 1911, before World War I. And it started in Liverpool, England, in what is known as the Royal Liver Building. I thought it was pronounced liver, but it's not. It's the Royal Liver Building, and it was the birthplace of life insurance. And this is also the world's first reinforced concrete building. And this is also the world's first hydronic radiant job. They did this job in 1911, and they installed 119,000 square feet of radiant walls. Imagine that, in 1911. We didn't even have the electric circulator until 1923. What they used to make this work back then, since this building would have had a steam engine to make electricity, was they used these turbine-powered De Laval horizontal split case, really big pumps to move the water around the building in 1911. So this is a landmark in Liverpool, England, the birthplace of the Beatles, or where the Beatles started out, and it is the world's first hydronic radiant heated job. lot of stuff gets started in England. This is a drawing from a magazine that was also published in 1911. And it talked about how the Vanderbilt family were building the East River homes for people that were suffering from tuberculosis. And when I saw this in an old magazine, I smiled to myself because I grew up in this apartment. When I was a little boy, my brother and I lived with my parents right in this apartment. And I had no idea that this building was built for health purposes by the Vanderbilts. And they chose to use hot water heat because it was a cleaner way of heating than steam heat back at the time. And this article explains the whole thing, and it was explained almost apologetically that they didn't use steam heat. They chose to use hot water heat because of its health benefits. And this made me so delighted because it meant that I was probably growing up in what may have been the first large-scale hot water heating project in New York City, if not America. So there you go. I was born to be a wet-head, and I'm happy to be one. Little side story for you there. This is the Royal Liver building again. These are the radiant walls. It wasn't actually in the walls, but they had these metal tray panels that were filled with a material called Dorado, which is like terrazzo. So you had these little tubes. You see the pipes going up into here. It would go back and forth and heat this Dorado and radiantly heat the space. In 1970, when they made the changes, they took down the panels. You could see the air dampers that brought in outside air that wafted across these hot rocks. And this is the radiant surface here. So it was 119,000 square feet of this stuff going in 1911. 1970 arrived, and all of the radiant was abandoned in favor of panel-type radiators. And they raised the floor to make all the piping work. So 1911 is our first radiant job. Back to England, back to 1912, on the other side of the country, in London, we have the Third Church of Christ Scientist, which is the very first job done with ceiling radiant in 1912. That same year, and also in London, we've got the Bank of England, and this is the installation as it went in with wrought iron pipe. And the reason why they did ceiling was they were able to use 185-degree water. And they did that because people don't walk on the ceiling. Nobody dances on the ceiling except Lionel Richie. Ha ha. So getting in touch with my inner 80s here. So this is all coming out of England. Radiant springs out of England and starts to head across to America, but we got to wait a while for it to arrive. And it arrives, of course, by courtesy of the British. And the British Embassy in Washington, D.C., which is not far from where my daughter lives, was built in 1930, and it went in with a radiant ceiling. And I've met people that have worked in this building and tell me that this is still up and running, and it's a radiant ceiling. So that is the oldest radiant heating system in America from 1930, done by the British. I always tip my hat when I drive past that place. 1930, we're in the depths of the Depression. And over there in England, 1933, we got some scientists working in a lab, and they're trying to improve plastics. They're trying to come up with new ways to make plastic. At the time, we had the original plastic, which was Bakelite, and that was pretty useful for making knobs on valves and things like that. But they wanted to come up with new types of plastics, so they were working with an autoclave and some chemicals that I can't pronounce because they're very long names. But they're working at very, very high pressure, and there was an accident. The autoclave actually exploded. And when it ruined the lab, didn't hurt anybody, but when they went back in to examine what had happened, they looked inside the autoclave and they found this white substance in there, which was a new type of plastic, and they named it polyethylene. And polyethylene was a plastic that was amazing to them, and they then tried to make it again, and they tried for a number of years to make it again, and weren't able to, and they kept bringing in bigger and bigger brains to try to figure this out. And finally they brought in a scientist who said, well, why don't we just repeat the original experiment? So they blew up the lab again, and sure enough, there was the polyethylene. So they said, okay, now we know how it's done. Now we just need more labs because we're going to keep exploding them. So no. They realized that the catalyst that made the reaction happen, made the magic happen, was the addition of oxygen when the stuff was at high pressure. So suddenly they were able to make polyethylene, and it starts to appear all over the place. And I first came in contact with polyethylene in 1964 at the New York World's Fair in New York, when I went to the Mold-A-Rama machine. This is a big deal when we were little kids. And I was 14 that year, but But this was the coolest thing because you put a quarter in there and you watch this molding machine make this stuff, and it was spewing out what was probably carcinogenic fumes. But we were okay with that. It was great, and then it would drop into this place over here, and you'd lift the slot and you'd reach in and grab your toy, and the toy was probably 350 degrees when you picked it up. But that was a time when people expected children to practice common sense, and there were fewer lawsuits. So polyethylene goes on to play this role in radiant heat for a while because they try to use it instead of the pipes that they were using at the time. But they find out that polyethylene will get mushy. It's a thermoplastic. As you heat it up, it's not going to stay stiff. It's going to get mushy, and that's not good if your controls on your boilers are not that stable. So polyethylene kind of sits in the background and becomes a plastic meant for other things other than heating. But it will show up again. 1933, the same year that they discovered polyethylene in England. In America, Frank Lloyd Wright creates the Usonian house, which is this type of a house that's going to work with radiant heat because he hated the way radiators look. So Mr. Frank Lloyd Wright is this brilliant architect that says, let's use wrought iron pipe, and I want you to notice how he's installing this stuff. It's laid within an inch or so of the surface. There's absolutely no insulation anywhere. And then when they put the concrete over it, it's the tubes are right there. So this is why these radiant systems did not last as long as people expected them to last. And nowadays, the right homes are, it's extremely expensive to try to retrofit with radiant heat. But they do it, but you don't want to destroy the historic nature of the building or the integrity of the building. But this is how they did it back then with the wrought iron pipe. We go to war. World War II, and suddenly the entire heating industry ceases to exist. There's no plumbing and heating being sold during World War II. Everything that's made of metal, everything that's made of porcelain is all going to the war effort, and everybody that's making stuff, that made stuff for the heating industry before, go into making stuff for the war. So people are actually ripping out radiators. We lost a lot of radiators during World War II. There was there was this movement toward just let's get the iron, let's get the steel, let's get everything out and have this big drive toward helping us win this war, make bombs and bullets and guns. So everything stops in the world of heating for those years. The war is over, everybody comes home, everybody's happy, woo-woo, VJ Day, Times Square, this is great, okay, let's get busy and let's make some babies. So we're going to get out there and we're going to have this baby boom. I'm a member of that. I was born in 1950, my big brother's born in 1948. All these kids show up at the same time. How many of them do you think touched that radiator? Okay, how many of you think that they touched that radiator more than once? I did, but not more than once. So we got all these babies, and now people want to get out of the cities, and they want to have a house to raise the kids. They want a yard, they want a fence, they want a dog and a cat. That's the American dream. So what happens is President Eisenhower comes around, and in 1956 we see the beginning of the Interstate Highway Act, which was built for military purposes. Not so much for the people, but to move armies around and to get people out of city centers in the event of a nuclear war. We were deathly afraid of the Soviets, so we wanted to get people out of cities, so we're going to build all these highways to act as spokes on the wheel, and this all becomes possible in 1956. And I think that this is one of the wonders of the world because I was born in 1950 and none of those roads existed. And to think that they're all there now, to me, is one of the most amazing feats of engineering that's ever been pulled off in the history of the world. So as they build these highways to get people out of the cities, they also begin to realize that people can live outside the city and commute into the city for their jobs. So we start to see the development of tract housing. And it pops up all over America. We're building these cookie cutter houses that are just going to be everywhere. And the cookie cutter houses are all going to get furnaces because it's now the 1950s. And furnaces are cheaper than boilers. And we're going to get out there and we're going to put in the furnaces all over America. And you start to see the change because prior to World War II, according to the U.S. Census, 50% of all the buildings in America were hydronically heated. And the other 50% were heated either with furnaces or gravity furnaces or stoves or fireplaces or weren't heated at all. But the hydronic share of the pie was 50% prior to World War II. And after World War II, it dropped to about 11%, where it remains to this day. So it is a very profitable non-growth business. That's what hydronics is. that includes both steam and hot water. So we see boilers appearing in places like Levittown in New York and Pennsylvania, where they're doing radiant heat. And this is the joy of Levittown. And I like this picture back when men were men, and the guy gets to sit in the easy chair, and the woman gets to squat, and he gets to smoke his stogie and blow smoke in the kid's face, and nobody cares. And he says, "Hey, go make me a sandwich." And my socks are slouched, but I don't care. So this is a different time, but he had radiant heat. He's living in Levittown. And he's got a fireplace here, and he's got radiant heat on the floor. And life's good for him and for her. Not so good for her, but you know what I mean. And the kid's going to grow up okay, so don't worry about it. So they're doing radiant with all different materials. This was copper, and it gets preformed in these bendable racks and gets put into walls as well. We're trying all sorts of different ways to do this back in the beginning. Wrought irons done by Mr. Frank Lloyd Wright. We even see the development of Bundy tube when copper becomes scarce, and Bundy tube comes out of the automotive industry, and Bundy tube was a composite pipe that was put together, and they decided that this is a great thing to use on radiant heating. And every so often somebody will show up on the wall at heatinghelp.com and say, "I've got this pipe that I can't connect to, I can't solder to, I can't weld to, I can't braze to. What the heck is it?" We say, "It's Bundy weld." It was a total disaster, but there's still some of it out there, so just be aware. In 1947, a Brit named Napier Adlam shows up, and he does all the original seminal research on radiant heating, and he writes this wonderful book called Radiant Heating, Radiant Cooling, and Snow Melting. And that's a book that's not that rare. You can probably get a copy on eBay or just look in an old bookstore, and it's a great read because he did all this early research on how radiant heat works and how it works with the human body. And Napier Adlam in 1947, in his book, he showed how they check people's temperatures. And this is an office worker, and they found she's 98.6 on the inside, but about 85 degrees on the outside. So he's checking her temperature, and they're trying to figure out how you make 85-degree surfaces to satisfy people that are 85 degrees. Today, this is called sexual harassment. In that day, it was called doing scientific research. So there you go. Because the fact is, she is producing enough BTUs to stay alive right there. So at her desk, she's producing about 500 BTUs per hour, as are you if you're sitting at a desk right now. So your body needs 100 BTUs per hour to maintain life. That's enough to keep your brain thinking, your diaphragm moving in and out, and your heart beating. You only need 100 BTUs per hour. The other 400 BTUs is a safety factor, and that must be shed. If it's not shed, you're going to die. And it's shed in a very specific way. We lose 100 BTUs per hour by evaporation. So she's perspiring right now because this guy's got this thing there, on her leg. But she's perspiring a little bit. When you perspire, the water evaporates and it takes heat with it. So she's losing 100 BTUs per hour right now. And if she were to pick up some of that paper on the desk and fan herself, she would lose another 100 BTUs per hour by convection. But fully 200 BTUs per hour, half the BTUs that she has to lose, she's losing by radiation. So her body and his body will radiate back and forth to anything that's cooler than themselves. And they'll pick up radiant heat from anything that's warmer than themselves. So right now, she may be feeling a little uncomfortable if she doesn't know this guy and he's in her space. That's why you do feel that kind of funny feeling when people get too close to you, because they're radiating heat at you and you're radiating heat at them. Might be okay for some people, might not be okay. So you can best experience radiant heat and how it works if you go to your local supermarket, because when you walk around the aisle, I want you to go first to the gadget aisle where you're going to find a thermometer. They sell it there. You don't have to buy it. You just stick it in it's a digital thermometer. Stick it in your shopping cart and take a walk. You can put it back later. Check the temperature. It's probably 70 degrees there in the supermarket. And then I want you to walk around to the produce aisle where you got these fruits and veggies, and you're going to notice that you feel a little chilly there, especially if it's summertime and you're walking around with flip-flops and a t-shirt and shorts. It's going to be a little chilly there. But while you're feeling a little chilly, as your body is radiating heat toward these cold surfaces, check the temperature on your thermometer. It's going to be 70 degrees in that aisle. And then go from there over to the frozen food aisle and feel the temperature there. You're going to feel real chilly in this aisle, but check the temperature of the air. It's 70 degrees. And Mr. Adlam, T. Napier Adlam, said that this is a phenomenon called cold 70. This is the feeling you get when the air temperature is 70 degrees, but the surfaces around you are cold, because your body is just going to throw radiant heat at these cold surfaces, and the body heat loss is going to make you feel uncomfortable. So you could be in a space that's being heated with a furnace that's throwing warm air at you, but the convection currents of the warm air moving across you will make you feel uncomfortable. And the cold surfaces, because air is a lousy medium to heat, say, cold glass, the cold surfaces will make you feel uncomfortable. But if you can heat the the floors with radiant heat, you'll feel more comfortable. So now with the shopping cart, go over there to the deli counter and stand in front of that rotisserie, and notice how the front of your body feels warm and the back of your body doesn't feel as warm. That's because this thing is throwing radiant energy at you. It's invisible. 1957, we find out that plastic pipe might be used for panel heating in this magazine, Domestic Engineering, back then. And in this article, they make mention of Bell & Gossett's plant in Morton Grove, Illinois, and they say that B&G had put in a snow melt system using polyethylene tubing. And at the time I saw this, I called my friends from Bell & Gossett and I said, do you guys realize that you put in a system in 1957 that if it's still up and running, it's probably the oldest plastic-based radiant system, snow melt system, or otherwise in America? And they said, we don't know anything about that. And they looked for all their records and they could find nothing about it. And I sent them this article where it says they did it. And they called the old timers that were retired and they said, does anybody know about this? And nobody did. So somewhere out there in Morton Grove, under some sidewalk or under some parking lot, there is plastic tubing that used to serve as the snow melt system for Bell & Gossett's plant. 65 rolls around, the same year the Beatles show up at Shea Stadium. Ah, what a day that was. You can get tickets for $4.50, or the highest price you could pay is $5.75 for a ticket. Imagine that. But in 1965, we also have a patent for this stuff that comes to be called PEX. And this is done by a brilliant man that I once met in Sweden when he came to a symposium that I was invited to that was being run by a company called what's now Uponor, but what was then Wurzbau. And this man's name was Thomas Engel. And Thomas Engel was not a scientist. Thomas Engel never really finished high school. Thomas Engel was in the German army during World War II. He was captured. He spent the war in an American prisoner of war camp and was released afterwards and went to work at various construction jobs and driving a taxi and just trying to make a living. But during the years he was an American prisoner of war, he read voraciously, and he was brilliant, and he read about plastics. They just captured his attention at that time, back in the 1940s. He was interested in polyethylene particularly, and he was trying to figure out a way to make polyethylene stronger, make it so that it had all the good properties of polyethylene, but it was not a thermoplastic. It would not get soft or mushy when it was heated. So he makes this breakthrough in the early 60s, and he manages to do that by getting the carbon atoms to link together and form this macromolecule, which actually has a memory. So if you form PEX in a tube and you were to melt it with a heat gun into a puddle and come back the next day, it's going to be a tube again in the exact same shape that it was before you melted it. And he did that in 1965. And then he goes around the world and he's trying to figure out, how can I sell this patent? Because he doesn't want to make this stuff. This guy just wants to invent things and sell the patents and get crazy rich, which he does. So he goes around and he shows this, and he tells a story when I met him about how he brings it to all these European industrial concerns, and nobody's interested in this new stuff, which he calls PEX, which stands for polyethylene cross-linked. Nobody's interested. So he goes back to Germany and he's kind of dejected, but he finds that his neighbor is a chicken farmer. Here we are with the chickens again. Remember in 1777 we had the first hydronic system go in as a gravity system in a chicken coop in Paris. And here we are with Thomas Engel delightfully dealing with his neighbor who's a chicken farmer. And the farmer says to him, Thomas, he says, I have a problem. He says, I'm raising the chickens, and we put the radiant pipe underneath the chickens to warm their hiney's and give us better eggs. He says, but the chickens are pooping on the pipe and it makes the pipe pop. And could you make pipe out of PEX so when the chicken poops on the PEX pipe don't pop? And Dr. Engel says, pipe? I can make pipe. This is great. So he gets an extrusion machine and he squirts out a bunch of pipe and he puts it under the chickens, and the chickens crap all over the pipe and it's impervious to chicken poop. So he says, okay, now I know how I'm going to sell this patent. I'm going to go to a guy that makes pipe. So he goes to this company in a town in Sweden called Virsbo, and the Wirsbo, and the town is actually named after the factory that has been there for hundreds of years. It's older than the town. The town has been making iron pipe for years and years and years. In fact, they paint all the houses the color of iron ore, and you've got these like picnic table colored houses, and you got these pine trees. It's just gorgeous. And he walks in and he says to them, I have one word for you: plastics. You've been doing it all wrong for all these years. You need to make the pipe out of plastic. And they said, why? And he says, because when the chicken poops on the pipe won't pop. And they said, Mr. Engel, there ain't enough chickens in this world to make this a viable business operation, so forget about it. So he doesn't want to give up, though. He says, but you could use it also for the radiant heat. And they said, why would we want to use it for radiant heat? He says, because that saves money. You don't heat the air with radiant heat. You just heat the people. The air stays the same temperature. That's where the savings is. You'll save fuel. But it's 1965. Who cares about what fuel cost in 1965? They're practically giving it away. So they said, no, we're not interested in that. But he doesn't want to give up. He's a stubborn man. So he says to them, you know what else you could do with this stuff? You could put it under a field, and you could warm the football stadium where they play the soccer, and you can increase the life of the season, the better grass, healthier for the players. And now the people at Wurzbo, they say, wow, now you're talking, because now we're seeing miles and miles and miles of this stuff if it's going into a stadium. So tell you what, you know what's coming to Germany where you live in a few years? The Olympics, the Munich Olympics. He says, why don't we talk to the Munich Olympics committee and see if we could put into Olympiad Stadium this turf warming system. And they do it. And this is the very first time in the history of the world when a hydronic-based radiant system goes in. It was done once before with an electric-based radiant system in Lambeau Field for the Green Bay Packers. But hydronics is used for the first time in a field in this Munich Olympics, which is remembered not for the radiant field, but for the PLO shooting up the Israeli camp. So that's history. So here we are at 72. We've proven through Napier-Adlam's British research that radiant heat saves money. It's 1972. And PEX is ready to go, and we're all good with that. And then the following year, 1973, we have the most serendipitous event in the history of heating, the OPEC oil embargo. So suddenly all over the world, everybody's waiting on lines, waiting to get gas, shooting each other, knifing each other, screaming at each other. The price of fuel goes way through the ceiling, and suddenly the interest in low temperature hydronics, radiant heating, PEX tubing picks up, and this stuff just takes off. And it takes off especially more in Europe than it does in America, because we're not ready for this yet, right? In America, we got our furnaces. We're happy with the furnaces. But in Europe, they're heating with these old radiators. They're doing like we were doing in our old cities. They're running 200-degree water through radiators that look like that. So suddenly, the German governments begin to step in and say, we're going to pass laws that say you can't use water that hot anymore. You got to lower the temperature, which makes radiant look even more appealing. And it also makes the radiator people get nervous. So they begin to create radiators like those panel radiators that I showed you in Mr. Geyer's office, the engineer. But we're going to have radiators that are bigger in surface and look better, so let's make radiators that look like that. So these are radiators that you'll see on trade shows in European cities, and each one of those is a radiator section, and you'll see radiators that look like that. And architects begin to get very interested in hydronic heating all of a sudden, because look at this stuff. That's a radiator. Oh my goodness, look at the thermostatic radiator valve over here. And that's a radiator. There's another TRV over here. Wow, we can turn this stuff into anything. We could have radiators that look like that. This becomes part of the design within a building. Wow, hydronics is the way to go. So all of Europe goes hydronic. There's no furnaces there. There's no steam there. It's against law to have steam over there. And at the same time, radiant works because heat does not rise. We're not heating the air. So Napier-Adlam, he wrote about the Liverpool Cathedral, which looks ancient, but it was started in 1920, and we had to pause for the war. It's finished in 1961. This is the Liverpool Cathedral, right near the Royal Liver Building. How cool is that? And this has radiant heat in it. It's not hydronic radiant heat. It's hot air being pushed underneath the stone floors. But Napier-Adlam did a survey on this and checked the temperatures, and he's checking the temperature up here, and he's checking the temperature down here. And in his book, this is what he shows. 4 feet from the floor, it's 60 degrees Fahrenheit, the air temperature. 58.5 degrees, 97 feet above the floor. So there's only a 1.5 degree drop in temperature from here to there, which tells us that with radiant heating, there is no convective movement of air. You don't get this rising hot air and pushing back. You don't see any ceiling fans in here trying to shove the air back down. So because there's no hot air up here at the ceiling, the heat loss of the building is less, because we're talking about the difference between the temperature inside the building and outside the building when we're figuring heat loss. So this is stuff that we knew in the 1940s. So we're positioned for this. This is again in Napier-Adlam's book. This is from Sarco. Sarco, the people that make all the steam equipment, Spirek, Sarco, were preeminent manufacturers of radiant heating systems at the time, and they used this Sarcotherm three-way valve, which took a chemical bulb sensor to the outside air, and a circulator that would put water either bypassing the system out to the radiant or back to the boiler to pick up heat. So a simple three-way valve. 1940s. And then comes Levittown. William Levitt, who was Time Magazine's Man of the Year at one point. He says, "No man who owns his own house and lot can be a communist. He has too much to do." How true is that? Keep in mind, we're in the middle of the Cold War now in 1946. All right, we got the bomb. The Soviets are about to get the bomb. So is the Chinese. So, this is where I grew up. I grew up on Long Island in a town called Hicksville, which is over here. Right now, Marianne and I live right over here. We're living right over here, right in this little circle. I'm showing you this because this is Hicksville. This is Bethpage, where we live. This is Levittown. Right? Levittown's right here. And none of this is separated by anything other than a road. So you cross the street, you're in another town. It's this suburban sprawl that goes everywhere. And Levittown was a famous place. Here I am in 1967, graduating from high school. Lived in that house, had hydronic heat, living in there with my brothers and my mother and father. Had convectors, and I love that place. 1967. Right, 1966, I'm going to Hicksville High School. Hicksville High School. And we go to the Battle of the Bands here, and the Commandos always played at the Battle of the Bands. They were this great band, and they're playing the senior, junior, senior mixer here. And here we got these guys that were terrific. And back here playing the keyboard is a young man by the name of Billy Joel. So he went to school with me. He sat next to me because he was a J, I was an H. We sat next to each other through most of junior high school and high school. And he told me when he was a young man that someday he's going to be more famous than Herman's Hermits. And I said, "No way." And he said, "Way." And Billy Joel was a big part of our lives back then because he played at all the dances. And, you know, he was a kid you'd sit on the curb with and drink beer with. And this is a good story because I remember this dance. I was there with my girlfriend, Maureen, who grew up in Westbury, which was another town that was just over across the street over there. And she and I were at this dance, and she was hot stuff. She was my high school honey. And Billy's singing a song here. The song he's singing right now is "Good Lovin'" by the Young Rascals, and he's doing his Felix Cavalieri invitation there. So Billy comes down after the song, and this is back when he had hair, and he goes up to my girlfriend Maureen, and he tips his hat, and he says, "How you doing?" So she says, "Fine, you know, I like your music." He says, "What are you doing?" She says, "Well, I'm with Danny. He's my boyfriend." So Billy looks at me, you know, he had never met my girlfriend before. So he tips his hat and he goes back to singing after he took a break. So she and I broke up right after high school, and I never saw her again. But I like to think that somewhere in the world she's smacking herself on the forehead and thinking she could have been one of those Mrs. Joels. You know, she had played her cards a little differently that day. But such is life. That's the way it happens. So anyway, this guy goes on to great fame and fortune, and he writes this song where he sings, you know, "Come out, Virginia, don't let me wait. You Catholic girls start much too late. Ah, sooner or later comes down to fate. Might as well be the one. Well, if you ever wondered about Virginia, here she is. Huh? Aren't you glad you took this course? That's Virginia from our high school yearbook." I don't know what happened to her either. But anyway, everybody's living there in Levittown, and that was the title of Billy Joel's song Allentown when he first wrote it, and we're living here in Levittown, because they built 17,000 houses, all identical on the inside, and they were building 30 houses a day, which is like this. None of this was here yesterday, and there it is today. They were finishing a house every 2 hours. They were building these things for mass production. There were people that did nothing but install doorknobs. There were people that did nothing but paint. There were people that did nothing but put in kitchen sinks. I mean, it was done that way. He wanted to bust unions. He just wanted people that just did one thing over and over and over again, and he was good at it. So it opens up on July 1st, 1947, and they sell these first houses, and there's 17,000 of them there, and they're all basically the same, and everybody's moving in at the same time. All these GIs are coming back from the war, and they're going out there and they're all buying houses. Everybody's got kids. They're all moving into these houses all at the same time. And, people would come home from work and they'd be half in the bag from being on the commuter train, and they'd pull into the wrong driveway. And I guess that's the way a lot of new relationships began that way when you think back on it. And I remember my father once dropping me off to sell Boy Scout candy canes at Christmas. And I went down one of these blocks and got lost around the corner. And it took him a couple of hours to find me. So they would build these Levitt houses. The total price was $7,990, and there were 5 architectural styles, but they were completely identical on the inside. So you can go and buy a house that looks like this or a house that looks like that, and it's just the same on the inside, your choice. When we were first married, we lived in an apartment that was the second floor of this Levitt house here, and there was another couple that lived downstairs here, and they had the radiant heat. We had convectors up there, and there was an oil tank buried under the lawn here. The landlord didn't live here, and he would frequently run us out of oil. And when he ran us out of oil, we'd feel it right upstairs. You wake up in the morning and it's cold up there, and I'd go downstairs and knock on my neighbor's door, and I'd say, we're out of oil, and he'd say, we are? And he wouldn't know, because he's living on this hot rock, which took a week to get warm in the fall and a week to cool down in the spring, but he never noticed it because of the radiant heat. And Mr. Levitt, when he was thinking about building Levittown, he went to this White Castle here, and the kid slid open the window to give him his burgers, and Mr. Levitt said, what's this? And the guy says, burgers. And he said, no, not the burgers, this that you're sliding back and forth. He says, it's a window. And this was the first time that sliding glass windows were used. They were used in White Castle. So he found out where they were made, and all the houses in Levittown got those windows. He also went to John's Manville, and he said, I'm looking for something that's cheaper than plywood, because that's too expensive. So John Manville comes up with a material called color bestis sidewall, which is basically sheets of asbestos. The house Marianne and I live in right now is made out of this stuff. So these people are all excited because they're moving into a house that's made out of asbestos. But this is at a time when asbestos was still our friend, so go figure. Oh, and there's the lady happy in her Levitt house, and she's doing the housework, and just leave the baby out on the front lawn. What could possibly go wrong? So what a time of innocence. And you can see the house trap is here buried under the lawn, and the oil tank is buried right underneath the window right there, right in the lawn. It's a 275-degree tank, not enclosed in anything but dirt. So here we are. This is the layout for the Levitt house. You can see that it's got this fireplace that's open on both sides. So if you're sitting in the kitchen, you could look in the fireplace, and you're sitting in the living room, the same thing. And it says the oil burner is mounted on the top of the washer. So the oil burner was there, and the oil burner, meaning the boiler, each one of these 17,000 houses were oil-fired. Pretty much they still are, because there's no gas there in Levittown. And they used the boiler made by either General Electric or by York Shipley, which was called a low York. That one sat on the floor. So the tank was buried out on the lawn, and this, oh, by the way, is Billy Joel's house where he grew up in Levittown, and there's some tourists going by to take a picture of it, such as it was. This is from Life magazine, and they show you how the Levitt houses were assembled from pieces that were just dropped on the site and then just quickly put together. But I want you to notice the slab, because there's not a bit of insulation anywhere around the perimeter, and there's no insulation underneath it. This is the Levitt slab. Before the concrete was poured, they used copper tubing, bendable copper tubing. They laid wooden 2x4s on the ground. They nailed the tubing to the wooden 2x4s to keep it from shifting, and then they just poured concrete right over that. And when those wooden boards cracked or rotted away from the soil that they were sitting on, because there's no vapor barrier underneath this, the slab would settle right where the wood used to be, and the tubes would begin to crack. So now we had a problem, because the floor would leak down, wouldn't leak up, it wouldn't show up as a wet spot on the floor, it would leak down into the ground, and the people would just notice that the heat's not right, and the water bill's going way up. So they would call up a local plumber and they would advertise in the papers, the penny savers. So in 1958, J.D. Brower said, "This is the radiant heating layout of your Levitt house. Save it so you'll know where the pipes are. Here's your house trap buried in the lawn. Here's your oil tank here buried under here with the lines going up to your boiler that's mounted above the washing machine." And the plumbers would then go out and they would crawl around on the ground and they would listen for the leaks with the back end of a screwdriver, or if they were sharp, they'd use a stethoscope to hear the water flowing where it shouldn't be. And one old timer told me that a woman told him, the housewife, she told him, "Oh, I could show you where that leak is, and fast and easy." So he says, "Well, how?" And she says, "Well, sit down and I'll show you." So she puts him at the kitchen table and she gets a damp mop and a bucket and she mops the floor. And he watches her do this. And then she goes over and she turns up the heat. She says, "I always run the heat to dry the floor before the kids get home so they don't mess it up." And she says, "I noticed that the floor always dried in these lines. I guess that's where the pipes are. But over here you can see it's drying in a big circle. So that must be where the pipes are broken." And sure enough, that's exactly what he found. So he says, you can learn something if you just listen to people that don't know anything about heating. Sometimes it's just common sense that helps you out on a job. So they used, say, the York Shipley boiler or the General Electric boiler, and they all worked the same way. They'd come out of the ground out of the slab with the pipes and into a manifold, and they'd go into a Bell & Gossett Series 100, and they would either go back into the boiler, this is a 3/4 inch pipe, or they'd go around the boiler and join up with water coming out of the boiler to go back into the slab. So the boiler is maintaining 180-degree water all the time because it's operating on a tankless coil for domestic hot water. The way they get the bypass to work is right here in this T, they have a 3/4 by 1/8 inch bushing, which came to be known as the Jal fitting, J-A-L, after Erwin Jelinek, who was the heating engineer who designed this system for Mr. Levitt. So that would be here on the side of the T. And whatever was coming out of the Series 100 that would fit through that 1/8 inch hole would go into the boiler and the balance would bypass. And Mr. Jelinek figured out that set up this way, if you maintained 180-degree water on the boiler, you would get 140-degree water going out to the tubing, which would give you 50 BTUs per square foot in the Levitt house, which seems like a lot by today's standards, but keep in mind it's the 50s and 60s and people like to put down rugs, even shag rugs, and they needed to push the heat through that. So that's the way it worked. And since it did have a tankless coil, it was kind of a funny aside to this because, we were living in one of these houses and the coil would get fouled. So you'd call your oil company where you had a service contract and you'd say, "I want you to come out here and service this." And the service contracts were always free if you bought the oil. And they said, "Well, we don't clean coils. You got to call a company and they're going to charge you for that." I said, "Well, I don't want to pay. I'll switch oil companies." So the oil company would send out a mechanic and he'd come out and boost the aquastat from 180 up to 200, which gave you plenty of hot water in your fouled domestic hot water coil, but it also raised the temperature going out to the floor. So we had these black builder's tiles made out of asbestos as well, and the glue would melt, and you'd be kicking these tiles around all over the place, and the pets would be up on the furniture, the kids would be screaming when they tried to walk on it. It wasn't the easiest system in the world to live with. So there's the tubing, they chop it up to get at it, and that's what it looks like. And one thing about Levittown is today, the guys that work there in the town on the boilers, they estimate there's probably about 5% of the houses still have this radiant system. And they know which ones they are too, because in the winter, there's never any snow within 5 feet of the house. And you will see tulips blooming in February there in Levittown. So that's the tubing, and it went off to this GE boiler here. We moved the stove out of the way to get at there's the tubing going down into the floor. And when we pull this cover off, what you find here is the General Electric oil-fired boiler, which had a burner that fired straight down. This is a pretty good boiler. It fired straight down and vented out the bottom. All the equipment is there. Everything is on this shelf. And Weil-McLean actually makes a boiler designed to fit specifically on that shelf. So they have a boiler called the Levittown boiler that will fit in that space. And the guys that do this work will get in there, rip the old one out, put this new one in. One guy will do that whole job in one day. This is York Shipley boiler. So there's a cover that goes over this, but that's what it looks like. And Peerless makes a boiler that fits in that footprint, so you can get everything in there, get the cover back on it, and just be there in Levittown. So time goes by, and the old timers found out that mopping the floor or listening to the floor, that's something that kind of goes by the wayside now that we've got these FLIR guns and but those are a little pricey too. But, in my magazine writing at one point, I wrote a story about finding the leaks by mopping the floor. And I asked several old-timers if that was the way they did it. And, I wrote it up as a great way to do it and took full credit for the method since, if you steal from one person, it's called plagiarism. But if you steal from everybody, that's called research. So I'm a big believer in research. And I wrote about that. But that prompted an old-time plumber to call me up and say, okay, big shot, what do you do in the rooms that have rugs, like the bedroom and the living room? You can't mop that, can you? How do you find a leak in there? So I hemmed and hawed for a while, and finally he left me off the hook, and he laughed, and he says, let me tell you something. He says, every old plumber that worked in Levittown had their own special piece of equipment. He says, and we walked in there, and the older and fatter that piece of equipment was, the better off we were. He says, because you just take your piece of equipment and you put it down on the floor. You make sure there's no sunlight shining through any of the windows, and you let the piece of equipment go through the house, and that equipment is going to find a leak every single time, and she'll lay right down on it, and all you got to do is move it and chop up the floor. I said, that's amazing. What do you call that method? He says, well, that, my son, is called a CAT scan. So keep that in mind. So with that, we will end our conversation about Classic Hydronics. I hope you had fun. And you can also, if you need instant answers, just go on the wall at heatinghelp.com and go in there. There's thousands and thousands of people in there that are far smarter than I am with way more experience. And they are happy to answer your question, usually in less than a minute. So thanks for listening to me for all this time. I appreciate it. And go get 'em.